हेलो दोस्तों, तो आज हम करने वाले हैं आयरन कार्बन फेज डायग्राम। बहुत ही ज्यादा इंपॉर्टेंट टॉपिक है और आपको आराम से समझना पड़ेगा और पूरा कंप्लीट समझ आ जाएगा। पहले मैंने वीडियो बना रखी है, वो बहुत पुरानी है, ठीक है। वहां पे आयरन साहब स्टील, ठीक है। अभी थोड़ा सा यूज करना मुझे इसका कम आता है, अगर मैं बीच में अटकता हूं तो नो प्रॉब्लम। अब स्टील बनाना ही क्यों है? क्योंकि भाई साहब हमारे पास जब आयरन होता है ना, आयरन अकेला इतना अच्छा नहीं होता। सबसे बड़ी मेन बात क्या, रस्ट लग जाती है उसके। क्या लग जाती है? रस्ट लग जाती है। वहां पे हमारे पास जंग लग जाती है। और इतना अच्छी क्वालिटी का मतलब क्या है? क्वालिटी का मतलब है हमारे पास इसकी स्ट्रेंथ की बात करें, स्ट्रेंथ कितनी है उसकी डक्टिलिटी कितनी है, ठीक है। देखो ये सारी टर्म जो है ना वो आपको पहले पता होना चाहिए। ये सब कुछ डक्टिलिटी क्या है, हार्ड सारी क्वालिटी चीज का अलग अलग यूज है। अब देखोगे तो आयरन कहां नहीं आपको देखने को मिलता। स्टील की बात करें तो कहां नहीं देखने को मिलता। बर्तन ले लीजिए स्टील के, वहां भी है। स्केल रूल ले लीजिए, हमारे पास जो स्केल होता है, स्केल ले लीजिए, वो भी हमारे पास क्या है, स्टील का बना हुआ है। बाइक के शॉकर, बाइक का हैंडल, कितने तरह के स्प्रिंग्स हैं जो हमारे पास यहाँ पे बने होते हैं स्टील के, ठीक है। मतलब की जाएगा। मान लो हैंडल अगर बाइक हमें ऐसा नहीं, मतलब ये चीज हैंडल में टफ नहीं है कि आयरन के अंदर अगर कार्बन मिक्स कर दिया जाए, और ये कार्बन खेल खेलता है सिर्फ परसेंटेज के बेस पे। कितने परसेंट कार्बन डालना है, ये बहुत बड़ा खेल है दुनिया का। कि कार्बन की 0.1% से, ठीक है, और कहां तक, सिर्फ 2%। 100 ग्राम आप स्टील बना रहे हैं तो उसमें से वो इसी का बहुत टेंशन होती है, स्क्रीनशॉट मतलब वो नती है, इतनी ज्यादा मैटर करती है कि हल्का सा भी आपने चेंज किया तो वही क्वालिटी चेंज हो जाएगी। आपने हीट ट्रीटमेंट उसका अलग कर दिया तो अलग क्वालिटी आ जाएगी। तो ये क्वालिटीज जो है, इस सारे को समझने के लिए हमें क्या करना पड़ेगा, हमें आयरन कार्बन डायग्राम को समझना पड़ेगा। अब इसमें क्या करेंगे, यहां पे हम बनाएंगे आयरन कार्बन डायग्राम बनाएंगे, और इस आयरन कार्बन डायग्राम में यहां पे इस लाइन पे हम क्या रखेंगे, कार्बन परसेंटेज वेट के हिसाब से कितनी है यहाँ पे, ठीक है। वेट के अकॉर्डिंग आयरन में हमने मिलाना है कार्बन, ठीक है। बात समझ आएगी, सिंपल सी है। लेकिन इसमें एक बहुत बड़ा फंडा है। बहुत बड़ा फंडा क्या है, नेक्स्ट एक और आ जाते हैं यहाँ पे। अब फंडा ये है कि कार्बन ऐसे इसके अंदर नहीं जाएगा, कार्बन आयरन के अंदर ऐसे नहीं जाएगा, ठीक है। हमें कुछ करना पड़ेगा, हम क्या करना पड़ेगा, उसको गर्म करना पड़ेगा। आयरन वैसे ही पड़ा है तो हम कहेंगे इसके अंदर जा घुल जा, नहीं घुलेगा। कार्बन उसके अंदर जा नहीं जाएगा, ठीक है। अब कार्बन को आयरन के अंदर डालने के लिए हमें उसको गर्म करना पड़ेगा, और जितना गर्म ज्यादा करते रहते हो उसके अकॉर्डिंग उसकी सॉल्युबिलिटी, मतलब उसके अंदर घुलनशीलता, कार्बन जो है आयरन के अंदर घुलने लग जाएगा, ज्यादा से ज्यादा उसके अंदर मिक्स होना स्टार्ट हो जाएगा। वास्तव में तो टेंपरेचर के अकॉर्डिंग, जैसे मैंने पहले भी एग्जांपल दिया है कि पानी में चीनी घोलना चाहते हो आप, तो चीनी 1 चम्मच 2 चम्मच 3 चम्मच घोलोगे, उसके बाद रुक जाएगा कि और नहीं घुलने, भाई पानी का और नहीं घुल सकता। आप पानी को गर्म कर दो, पानी को जैसे ही गर्म करोगे तो वहां पे चीनी और ज्यादा आप उसके अंदर ऐड करना स्टार्ट कर दोगे। आप कहोगे यार अभी तो तू कर रहा था, बस पानी का अभी तो तू कर रहा था, बस अब कैसे दोबारा चीनी घुलने लगी। तो इसका कारण ये है कि टेंपरेचर आपने इंक्रीज कर दिया और उसकी सॉल्युबिलिटी बढ़ गई, ठीक है। सॉल्युबिलिटी बढ़ गई, अब वो और ज्यादा कार्बन इसमें ऐड कर सकता है। बात समझ आ गई। कार्बन ऐड करना है तो टेंपरेचर राइज करना पड़ेगा। तो समझने की उसमें बहुत अच्छी अंग्रेजों के द्वारा बनाई हुई वीडियो है, बहुत अच्छी है, उसको जरूर देखना आपने। उसमें मैंने आपको सारा कुछ समझाया हुआ चीजों के बारे में। देखिए हमें क्वालिटी चेंज करनी है, लेकिन क्वालिटी चेंज करें कैसे? अब वर्ड क्या है कि हमें क्या चेंज करना है, क्वालिटी चेंज करनी है। अब क्वालिटी चेंज हो तो हो कैसे? हमें तो ये पता है कि आयरन जो है, जो हमें नेचर से आयरन मिल रहा है, Fe मिल रहा है, वो मिल रहा है हमें BCC में। अब ये BCC क्या होता है ये भी आपको पता होना चाहिए, बॉडी सेंटर क्यूबिक। बॉडी सेंटर क्यूबिक अगर आपने पूरा सिलेबस नहीं करा तो आपको प्रॉब्लम आ सकती है। प्लीज पूरा सिलेबस शुरू करना। BCC क्या है, इससे ऊपर वाले सब मैंने जो चैप्टर है उसमें करवाया हुआ है। तो BCC बॉडी सेंटर क्यूबिक हमारे पास कुछ इस तरह का होता है, ठीक है। इस तरह का होता है हमारे पास, और इसमें हमारे पास अलग अलग यहाँ पे एटम एक एटम जो, ठीक है, खासियत ये। हमें क्या करना पड़ेगा, हमें चेंजेस हार्ड क्यों है, ये BCC हार्ड क्यों है, मेन काम ये कारण ये है कि इसके अंदर जो आयरन के अंदर देखेंगे हम, तो आयरन के अंदर हमारे पास जो ग्रेन साइजेस होंगे ना वो बड़े बड़े होंगे, इस तरह से ग्रेन्स होंगे, वो बड़े बड़े ग्रेन्स होंगे, ठीक है। इस तरह से बड़े बड़े ग्रेन्स होंगे, ठीक है, आप समझ लें। तो इस वो आगे एक वीडियो है बहुत अच्छी है, उससे आपको बहुत अच्छा क्लियर हो जाएगा। हमें करना क्या है, बेसिक फंडा करना क्या है, हमें करना है कि हमें आयरन ऐड करना है, आयरन के अंदर कार्बन ऐड करना है, और उसके कारण होगा क्या, जब हम टेंपरेचर राइज करेंगे और उसमें कार्बन ऐड करेंगे, टेंपरेचर राइज करना है और उसमें कार्बन ऐड करना है, तो उसमें क्या है कि हमारा जो BCC है वो FCC में चेंज हो जाएगा। जब हम उसका टेंपरेचर बढ़ाते हैं ना तो वो FCC में चेंज हो जाता है, फेस सेंटर क्यूबिक में चेंज हो जाता है, FCC में चेंज हो जाएगा, ठीक है। पहले हमने टेंपरेचर बढ़ाया तो हमारे पास BCC से वो बदल गया FCC से, FCC में। अब FCC में चेंज हो गया तो उसमें FCC में चेंज होने के कारण हमारे पास यहाँ पे चेंज आ गया, उसके क्रिस्टल स्ट्रक्चर ही चेंज हो गए, उसके अंदर नए क्रिस्टल बनने स्टार्ट हो गए, जिसके कारण क्या कहते हैं हम उसको रिक्रिस्टलाइजेशन टेंपरेचर कहते हैं। हम कहते हैं रिक्रिस्टलाइजेशन टेंपरेचर है, BCC से नए FCC बन गया है। अब इसमें चेंजेस आ गए हैं, नया स्ट्रक्चर चेंज हो गया। मतलब आप सोच के देखो, एटम भागते हैं, वो खेल देखो कितना अच्छा है कि हम इस यहाँ पे मैं आपको बना के दिखाता हूं कि मेरे पास यहाँ पे भगवान जी ने बोला, ठीक है, जो भी आप में से कई गुस्सा करते होंगे कि आप इसमें क्या बार-बार बीच में भगवान, कई ना ऐसे हैं जो इन चीजों में विश्वास नहीं करते, तो मैं नेचर वर्ड यूज कर लेता हूं। तो जहां मैं भगवान बोलता हूं तो मेरी आदत है, उसका मतलब मेरा ये है नेचर, जो जिसने ये बनाया, मुझे नहीं पता क्या है क्या नहीं, ये डिबेट नहीं है। जिसने भी ये बनाया, नेचर ने बनाया FCC मतलब आयरन को BCC ऐसा बना दिया। लेकिन हाँ एक चीज देखो कि एटम बात मानते हैं, ठीक है, एटम बात मानते हैं। जब हमने टेंपरेचर बढ़ाया एटम भागने स्टार्ट हो गए, भागो, नई स्ट्रक्चर बनानी पड़ेगी। क्या चीज है, क्या खतरनाक चीज है, नई चीज बन गई, नया स्ट्रक्चर बन गया। बात समझ के देखो, दिमाग में सोच के देखो, जो एटम सेंटर में था ऐसे एटम थे, इस तरह के थे, अब फेस पे आ गए, यहाँ पे अब अच्छा नहीं बनेगा इसमें, ठीक, यहाँ पे अच्छा नहीं बना पाएगा, तो ये तो इस तरह का आ गया, BCC से FCC में चेंज हो गया, भाग गया, भागो। फिर दोबारा आपने ठंडा कर दिया, भाई पंगा डाल दिया, फिर से दोबारा बेचारा वो FCC से BCC में, BCC से FCC में, FCC से BC में। फायदा हमें क्या फायदा, हमें एक फायदा ये मिलेगा कि जब हमने स्टार्टिंग जब की तो उसके ग्रेन साइजेस बहुत बड़े थे, इस तरह से थे, बड़े बड़े ग्रेन साइजेस थे, ग्रेन्स मोटे मोटे बड़े बड़े थे, जिसको हम इंग्लिश में कहेंगे कोर्स, लेकिन उसके जो अब ग्रेन्स बने वो छोटे छोटे बन गए, फाइन ग्रेन्स बन गए। और ग्रेन्स का ही सारा खेल है भाई साहब, सारा का सारा खेल ग्रेन्स का ही है। इस ग्रेन्स ने हमारे पास चेंजेस लाने, ये देखो वही है, लेकिन अब ग्रेन साइजेस चेंज हो गए, ठीक है। इसको आपको वीडियो के थ्रू बहुत अच्छा समझ आएगा। यहाँ बड़े बड़े ग्रेन्स, यहाँ छोटे ग्रेन्स, ये बिफोर है, बिफोर सारा कुछ करने से बिफोर, ठीक है। चेंजेस आएंगे, उसमें चेंजेस आएंगे तो हमारे पास इस तरह से फाइन ग्रेन्स बनेंगे। फाइन ग्रेन्स जो होते हैं वो बेटर होते हैं, इसमें डक्टिलिटी अच्छी होती है, इसमें स्ट्रेंथ अच्छी होती है। जितना हमारे पास ग्रेन साइजेस चेंज होंगे उतना ज्यादा हमारे लिए अच्छा है। तो ग्रेन साइजेस को चेंज करना ही हमारा मकसद होगा, ग्रेन साइज के साथ खेलना कि भाई इस तरह का आजा मेरी बात मान, इस तरह का बन, वो बन जाएगा मेरे भाई, इंसान है, आयरन कहता है हम किसकी बात मान सकते हैं, ठीक है। अब हमें टेंशन नहीं है, हमें सारा कुछ देखने को मिल सकता है, वैसा का वैसा पड़ा है, पहले जैसा नहीं कि रब कर दिया तो हो गया, ठीक है। अब देखो, अब हमें क्या समझना है कि ये मेन क्वालिटीज क्या है, इसमें मैं आपको यहाँ पे दिखाता हूँ आयरन कार्बन डायग्राम, प्लीज आप भी पहले बना लेना ताकि आपको भी थोड़ा सा एक्सप्लेनेशन समझ आ सके, ठीक है। सॉरी, यहाँ पे डेस्कटॉप, ओके, यहाँ पे आ जाते हैं। तो हमारे पास यहाँ से शुरू करते हैं सबसे पहले, तो मेरे पास यहाँ पे नोट करने वाली बात जो है वो ये है कि यहाँ से एक लाइन आ रही है, ये देखो ये लाइन आई, ये लाइन आती है थोड़ी टेढ़ी हो रही है, देखो टेढ़ी होगी, यहाँ तक आई, यहाँ तक आ गई। अब ये जो लाइन है, ये वाली लाइन है, जो वो लाइन जो है हमारे पास यहाँ पे मैक्सिमम कार्बन परसेंटेज कितनी ऐड हो सकती है उसको दिखा रहा है, ठीक है, उसको दिखा रहा है। यहाँ पे मैं इसको दोबारा बनाता हूँ, ठीक है, दोबारा बना के आपको समझाता हूँ। ओके, थोड़ा सा इसमें यार अभी प्रॉब्लम आ रहा है, 0.025% है, 0.025% कार्बन इसके अंदर आ सकता है। और इसमें हमारे पास आगे जाके फिर देखो, फिर वापस इसी लाइन पे आ रहा है, ठीक है। इसके टेंपरेचर नोट करने, हमें जो टेंपरेचर नोट करने हैं वो सारे टेंपरेचर हमें नोट करने। मेन इसमें टेंपरेचर है 723 डिग्री सेंटीग्रेड, ये सबसे मेन टेंपरेचर है जो हमें समझना है, जो क्या कराएगा, रीक्रिस्टलाइजेशन टेंपरेचर कराएगा। इस अब मैं यहाँ पे सेम ना ये वाली चीज जो है ऊपर इसमें अपने वाले में बना के दिखाता हूँ आपको, ठीक है। तो यहाँ पे मेरे पास क्या है, ये कुछ इस तरह का, ठीक है। सॉरी, मैं इसको पेन ले लेता हूँ, अच्छा सा। यहाँ पे हमारे पास बहुत सारी ऑप्शन है, टेंशन नहीं आपको, ठीक है। आपका भाई कुछ और ही चीज बन गया, ठीक है, पढ़ास, ओके। यहाँ पे आ जाते हैं, ओके। तो ये जो लाइन है हमारे पास आएगी, वो आएगी 723 डिग्री, इतना खास बनाया होने वाला है, तो इसको हम यूज कर लेंगे, ओके। तो यहाँ आ जाते हैं, तो ये मेरे पास टेंपरेचर आ गया 723, 0.025% कार्बन, बताओ इतना कम, इतना कम, 0.025% कार्बन सिर्फ ऐड कर सकते हो। ये आयरन को हम आयरन को कह देते हैं फेराइट, ये लाइन जो होती है इसको फेराइट नहीं होता है इसके बारे में, तो ये फेराइट होता है, लेकिन बन जाता है लाइट, परलाइट जैसे भी आप बोलना चाहिए उसको बोल सकते हैं, परलाइट होते हैं। और इसकी जो शेप होगी वो जिस तरह की होगी, अगर ग्रेन ये है तो इसके अंदर यहाँ पे आपको यहाँ पे दिखेंगी लाइंस दिखेंगी, और ये जो लाइंस होती है ये कार्बन की लाइंस होती है, ये कार्बन है, तो ये वाला एरिया जो होगा आयरन, और ये जो लाइंस यहाँ पे दिखेंगी वो होगा हमारे पास कार्बन। दोनों को मिक्स करने के बाद हमारे पास परलाइट बनता है, दोनों को मिक्स करने के बाद परलाइट बनता है, तो हमारे पास ये जो एरिया होगा ये वाला सारा, ओके, परलाइट। सारे को नाम बताऊंगा, इस एरिया को हम, ठीक है, यहाँ पे आपको समझाता हूँ। ये घर बना हुआ है, ये घर बना हुआ है, लाइन में बने हुए, सारे लाइन में बने हुए, लेकिन यहाँ पे बॉर्डर है, यहाँ पे मान लीजिए कोई भी बॉर्डर, किसी देश का बॉर्डर है, किसी भी देश का हो सकता है, ठीक है। तो अगर मैं यहाँ से कहूँ तो मेरे घर से मैं कहूँगा अरे यार मेरे घर से जो मैं यहाँ पे ना एक लाइन यूज कर लेता हूँ, 3 है, एक भाई मेरा तो 2 किलोमीटर है, सबसे ज्यादा मुझे खतरा है। आंखों यार सबका अलग क्यों, क्योंकि भाई ये बॉर्डर की लाइन टेढ़ी है, मतलब इसको क्रॉस करने के लिए अलग अलग डिस्टेंस है, अलग अलग डिस्टेंस है। यहाँ पे मान लेते हैं कि यहाँ पे ये एक बॉर्डर, हम लोग इंडिया सबसे ज्यादा हमें तो इंडिया पाकिस्तान ही समझ आता है, तो क्योंकि बॉर्डर कई बार तो हम सोचते हैं नेपाल में तो ओपन पड़ा होता है बॉर्डर, हमें तो ये समझ आता है। तो ये मान लीजिए कि यहाँ पे पाकिस्तान का बॉर्डर है, मैं यहाँ पे एक बना देता हूँ, ठीक है, थोड़ा सा यहाँ पे बनाता हूँ, ये पाकिस्तान का बॉर्डर है, ये पाकिस्तान का बॉर्डर, ओके। यहाँ पे आ गया इंडिया, यहाँ पे आ गया पाकिस्तान, ठीक है, पाकिस्तान आ गया, पता नहीं किस बात की। ये आप सोचोगे सर 2 लाइन क्यों है, क्योंकि भाई नो मैन लैंड भी होता है, ये हमारा अगर फेंसिंग होती है, यहाँ पे हमारा जाल होता है, इनका जाल यहाँ बीच में कुछ भी नहीं होता, बीच में एक नो मैन लैंड रखते हैं कि इसमें कोई भी नहीं आएगा, ठीक है ना, आपका ना मेरा बीच में, तो हम यहाँ काम कर सकते हैं, यहाँ काम कर सकते हैं, तो हमारा बीच में एक बॉर्डर रहेगा, क्लियर, थोड़ा सा आइडिया आया, ठीक है। अब मेरे पास ये लाइन टेढ़ी का मतलब समझ आ गया होगा आपको, तो लाइन टेढ़ी का फायदा हमें क्या, इससे क्या हो जाएगा आपको सर, मतलब इसका क्या फायदा, इसका ये है कि भाई साहब अगर तो कार्बन परसेंटेज अलग अलग है, अगर आपकी कार्बन परसेंटेज यहाँ पे है 0, तो आपको क्या करना पड़ेगा, देखो ये टेंपरेचर चलता जाएगा चलता जाएगा चलता जाएगा, ये देखो इस तरह से आप क्या कर सकते हो, इस लाइन को पार करने के लिए आपको यहाँ से टेंपरेचर देखना पड़ेगा कि कितना टेंपरेचर है। अगर आपके पास कार्बन परसेंटेज 0.025 होगी तो आपको क्या करना पड़ेगा, इस लाइन को यहाँ से पार करना पड़ेगा, यहाँ से पार करना पड़ेगा। अगर आपके पास कार्बन परसेंट थोड़ी सी भी कम हुई तो आपको यहाँ से पार करना पड़ेगा। मतलब ऑस्टेनाइट बनाने के लिए कोई फिक्स टेंपरेचर नहीं है, टेंपरेचर फिक्स अकॉर्डिंग टू कार्बन होगा, कार्बन की कितनी परसेंटेज है उसके अकॉर्डिंगली टेंपरेचर होगा कि ऑस्टेनाइट में जाना है, ऑस्टेनाइट में जाना है तो भाई ये एक वहां से एक मैं ये कह सकता हूं कि कार्बन की परसेंटेज देखकर हम कहेंगे कितना डिग्री टेंपरेचर करें कि वो ऑस्टेनाइट में घुस जाए, ठीक है, बात समझे। क्योंकि अगर 0.025 हुआ तो 723 डिग्री है, काम खत्म, 723 डिग्री करो, ठीक है, मतलब 724 करो, वो भागेगा, ऑस्टेनाइट में भागना स्टार्ट हो जाएगा, उसके क्रिस्टल चेंज होने स्टार्ट हो जाएंगे। अगर कार्बन परसेंटेज कम हुई तो वो ऑस्टेनाइट में जाने के लिए 723 नहीं 730 740 780 900 डिग्री सेंटीग्रेड तक चाहिए होगा। तो हमें टेंपरेचर अकॉर्डिंग टू कार्बन परसेंटेज देखना होगा कि यहां से केस कैसे जाए, गॉट इट, बात समझ आई। कार्बन पर अब ये लाइन एक बार समझा रहा हूं, इतना जोर इसलिए लगा रहा हूं मेरे बेटा क्योंकि यही चलना है, यही लाइन चलनी है टेढ़ी मेढ़ी। मैं यहाँ पे ऐसे बना देता हूँ, मैं बताऊँ कार्बन परसेंटेज बताओ कितनी है, नहीं मैं आपको सर मुझे ना ऑस्टेनाइट बनाना है तो कितना टेंपरेचर रखूंगा भाई साहब, कार्बन परसेंटेज बताओ पहले इतने मत बोलो, मुझे पहले कार्बन परसेंट बोलो, आपको सर कार्बन परसेंट तो 0.025 है, अच्छा 0.025 है, ऐसे करो इसमें आप 723 डिग्री सेंटीग्रेड ऊपर ले जाओ, आपको ऑस्टेनाइट बनना स्टार्ट हो जाएगा। अच्छा ठीक है, आपको कैसे पता, मैं आयरन कार्बन डायग्राम समझाऊंगा, आयरन कार्बन डायग्राम आप कहोगे नहीं सर 0.0 कितना ज्यादा टेंपरेचर और ज्यादा टेंपरेचर और ज्यादा टेंपरेचर। अब देखो दूसरे पॉइंट पे आते हैं हम, वापस आयरन कार्बन डायग्राम में चलते हैं और वहां पे हम समझते हैं इन चीजों को और ज्यादा। ये लाइन समझ आ गई टेढ़ी, अब आपके दिमाग में आई कि सर अब ये लाइन कहां से आ गई और ये लाइन कहां से आ गई, बात समझिए थोड़ी सी। अब मैं आपको और ज्यादा आगे लेके चलता हूं और धीरे धीरे इन लाइनों के बारे में समझते हैं, ठीक है। ये लाइन कहां से आ गई, ये लाइन कहां से आ गई, तो 2 लाइन और हम यहां पे लगाएंगे और इसके अकॉर्डिंगली हम इसको समझेंगे, ठीक है। 2 लाइन और आती है हमारे पास, ठीक है, कौन कौन सी थी, एक ये वाला लाइन, ठीक है, एक ये वाला लाइन ऊपर से नीचे और ऐसे, ठीक है। तो मेरे पास आ जाएगा मेरे बेटा ये यहां से यहां और यहां से यहां, इस तरह से जाएगा। अब ये जो एरिया है ये ऑस्टेनाइट है। अब आप कहोगे सर ये क्या है, फिर ये क्या चीज आ गई बीच में, ये क्या चीज आ गई, तो ये चीज जो है यहां डॉटेड दिखाता हूं, ये नो मैन लैंड है, ये नो मैन लैंड है। अब एक चीज नोट करना कि अगर मेरे पास बीसीसी से एफसीसी बनेगा, बीसीसी से एफसीसी बनेगा, ऐसा तो नहीं है कि आपने जैसे ही टेंपरेचर किया रिक्रिस्टलाइजेशन टेंपरेचर, जैसे ही क्रिस्टल चेंज होने का टेंपरेचर आया तो झटके से मतलब ओ बीसीसी से एफसीसी हो गया, नहीं, बीसीसी थोड़ा सा एफसीसी बनेगा, फिर थोड़ा सा बनेगा, फिर थोड़ा सा बनेगा, फिर थोड़ा करते 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 सारा एफसीसी हो जाएगा। इट विल टेक टाइम, कोई चीज अचानक से नहीं बनती, टाइम तो लगता है। अगर आप कहोगे सर मैंने स्कूल बिल्डिंग तैयार करनी कल क्या कर दूं, ऐसे होना होता है 6 महीने लग जाएंगे, ठीक है, 6 महीने लग जाएंगे, कुछ काम होने में टाइम लगता है, नहीं बढ़ेंगे, धीरे धीरे चलेगा, ऐसा होना चलेगा। सीसी से एफसीसी बनता रहेगा, पूरा एफसीसी अभी नहीं बनेगा जब तक इस लाइन को क्रॉस नहीं कर जाते, इस लाइन को क्रॉस नहीं कर जाते। मतलब क्या है कि ये देखो अगर मेरे पास इतने रेंज जो है वो बीसीसी की एफसीसी, इसके बाद जो लाइन आएगी ये क्रॉस करनी पड़ेगी हमें ऑस्टेनाइट में जाने के लिए, ऑस्टेनाइट में जाने के लिए। गॉट माय पॉइंट और नॉट, प्लीज समझ आ गया होगा, ठीक है। अब इन लाइंस के ना कोई नाम है, देखो यहाँ पे नाम लिखे होते हैं, कहीं भी देखोगे तो हमारे पास यहाँ पे A3 लाइन है, ठीक है, सॉरी A3 लाइन है, ACM लाइन है, ये नाम है ना। तो ये नाम जो है वो लाइंस को दिए गए हैं कि आपने किसको, कि जीसीसी के अंदर जो घुलनशीलता है कार्बन की वो सिर्फ कितनी है 0.025। लेकिन अगर आपने एफसीसी बना दिया तो एफसीसी जब बनेगा तो हमारे पास एफसीसी बनेगा तो उसकी घुलनशीलता हो जाएगी 0.83 कार्बन परसेंटेज की। कार्बन परसेंटेज जब 0.83 घुल सकता है। और एक और चीज कहते हैं चौरस्ता, चौरस्ता होता है ना किसी भी चीज का चौरस्ता होता है। तो मैं आपको चौरस्ता दिखाता हूं, देखो हमने क्रॉस करना था यहां से, ये क्रॉस करना था सारा, ये देखो यहां से एक लाइन देखो, जो ये लाइन है, ये वाला पॉइंट यहां सीधा ऑस्टेनाइट के अंदर घुस रहे हैं, यहां से देखो ये ऑस्टेनाइट के अंदर सीधा घुस रहे हैं ना यहां से। तो ये एक पॉइंट देखो कितना नीचे है और वो 723 डिग्री सेंटीग्रेड पर ही है यहाँ पे। ये कुछ पॉइंट्स अलग होते हैं जो मैं आपको सारा समझाऊंगा, ठीक है। इसमें भी आपको पूरा समझने को मिलेगा कि ये पॉइंट क्या है, ये सारे क्या है, ठीक है। तो हमारे पास ये टेंपरेचर, ये वाला क्या है और ये वाला क्या है, ये सारा कुछ हमें बताना है। बहुत बड़ा है, वो छोटी मोटी चीज नहीं है जो मैं समझा रहा हूँ, ये बहुत बड़ी चीज है। इसको समझने में करने में बहुत टाइम लगता है, इसलिए मैं धीरे चल रहा हूँ। आप तो स्पीड बढ़ा सकते हो, वीडियो की स्पीड बढ़ा लेना, ठीक है। बोर नहीं हुए तो चलते रहो, आराम से चलते रहो। ओके, मुझे लगता है पानी की जरूरत पड़ गई है, ठीक है। इसकी साइड तो मेरे पास कुछ इस तरह से होगा, ये देखो। तो ये वाला पॉइंट आ गया, तो ये पॉइंट क्या है, यहाँ पे कार्बन परसेंटेज कितनी घुलनशीलता है 0.83% कार्बन। अभी भी देखो, अभी भी कुछ ज्यादा नहीं हुआ, 1% भी नहीं पहुंचा, अभी सिर्फ 0.83, कितना कम होता है। यहाँ टीचर तो मैं बनना ही चाहता था और बचपन से ये चीजें सोचता था कि ऐसा हो ना, ऐसा हो सके, इजी भी निकाल लिया था हमें ACM, ठीक है। याद कर लेना, इन लाइंस पे नाम याद कर लेना पड़ता है। और वो बनता है डेल्टा आयरन बनता है हमारे पास। तीसरी चीज बनती है हमारे पास, क्या बना, हमारे पास सबसे पहले परलाइट बना, ऑस्टेनाइट बनेगा, उसके बाद डेल्टा आयरन बनेगा। और वो टेंपरेचर जो होंगे, वो लाइंस जो होंगी, वो कुछ इस तरह से, ये देखिए ये लाइन अब इस तरह से टेढ़ी जा रही है यहाँ पे। और ये हमारे पास ये वाला एरिया जो होता है, ये छोटा सा, ये डेल्टा आयरन होता है। जो वो घुलनशीलता डेल्टा आयरन में हमारे पास जो है वो हमारे पास कितनी है 0.16, ठीक है। अब मेरे पास वापस आ जाते हैं यहाँ पे, तो यहाँ पे आ जाते हैं, ओके। यहाँ पे इस तरह से ये जो है भाई साहब वो है डेल्टा आयरन, ठीक है। और ये जो हमारे पास टेंपरेचर है वो है 1400 डिग्री सेंटीग्रेड, 1400 डिग्री सेंटीग्रेड, ओके। अब देखो मैंने पहले भी आपको, चल डेल्टा ऐसे नहीं मिलेगा, ये क्या देगा, ये इंडिया ये पाकिस्तान, तो ये बीच का एरिया जो है वो दोनों का मिक्सअप, ये इंडिया ये पाकिस्तान दोनों का मिक्सअप। यहाँ पे हमारे पास क्या है, और ऑस्टेनाइट को गामा आयरन भी बोलते हैं, ये भी याद कर लेना। ये मैंने आपको बताया नहीं, सॉरी, ये मेरी थोड़ी गलती है, इसको नाम याद करना है हमने, गामा आयरन। और ये गामा डेल्टा में थोड़ा सा अच्छा लिख दूं इसको चाहे, ठीक है। अब हम किसी से डरते नहीं है, ठीक है। हो जाता है इसमें यार डिलीट, कहीं और से भी डिलीट हो जाता है, ठीक है। तो यहाँ ये आ गया अल्फा प्लस गामा, दोनों का मिक्सअप। यहाँ डेल्टा यहाँ गामा, तो यहाँ क्या होगा, डेल्टा प्लस गामा, छोटा सा लिखे, डेल्टा प्लस गामा, दोनों का मिक्सअप होगा। और ये अकेला क्या होगा, डेल्टा होगा, ठीक है। आसपास कई बार बुक्स में अलग होता है। ये सारा लिक्विड हमारे पास लाइन जो है वो ये देखिए, ये वाली लाइन जा रही है, ये वाली, ठीक है। 1539 है, एक्जेक्टली लिखना, 1540 नहीं 1539 है। ये वाली लाइन जो है ये यहाँ जा रही है और प्लस ये लाइन आगे जा रही है, ठीक है। तो मेरे पास ये नोट करने के लिए यहाँ पे है, ठीक है, लिक्विड। तो यहाँ ये देखो, ये है लिक्विड, ये है डेल्टा, यहाँ क्या होगा, लिक्विड प्लस डेल्टा। बताओ कितना आसान है, यहाँ क्या होगा, लिक्विड प्लस डेल्टा। और ये मेरे पास यहाँ से आया और ये आगे चला जाएगा, यहाँ पे ये लाइन यहाँ पे चली जाएगी इस तरह से, ठीक है। ये लिक्विड है, ये गामा है, तो ये क्या होगा, लिक्विड प्लस गामा, ठीक है। सॉरी यहाँ पे गामा आएगा, ओके, यहाँ पे गामा, कितना आसान है ना। देखो ये इन दोनों का मिक्सअप, ये इन दोनों का मिक्सअप, ये इन दोनों का मिक्सअप है, तो ये इस तरह से है। थोड़ी सी समझ आ रही है कि नहीं आ रही, ठीक है, बात समझ आ रही है। बहुत ज्यादा इंपॉर्टेंट चीजें हो रही है यहाँ पे आज। अब हमारे पास और कौन सा है, ये ACM लाइन भी आ गया, कुछ रह जाए तो हमें बाद में भी करेंगे, कोई प्रॉब्लम नहीं है, ठीक है। ये मेरे पास ओके, इसमें एक ये लाइन आप याद कर सकते हो कि A1 लाइन बोल देते हैं इसे, और यहाँ से ये वाली लाइन को A2 लाइन बोल देते हैं। आप मेरे साथ लिखते रहना, ठीक है, लिखते रहना, नहीं तो आपको प्रॉब्लम आ सकती है, ठीक है। और ये एरिया डिवाइडेड है, ये देखो ना, ये एरिया डिवाइडेड है। ये एरिया डिवाइडेड कैसे है वो भी मैं आपको यहीं पे समझाता हूं, ठीक है। यहाँ पे देखो परलाइट प्लस फेराइट लिखा है, यहाँ परलाइट प्लस सीमेंटाइट लिखा है। यहाँ सीमेंटाइट परलाइट करने की प्रोसेस करते हैं या क्वेंच कर देते हैं पानी के अंदर, ऑयल के अंदर। जैसे अगर हमने क्वेंच कर दिया किसी पानी के अंदर या ऑयल के अंदर, उसके कारण वो हार्ड बन जाता है, ठीक है, हार्ड बन। तो सीमेंट पता क्या होता है, पानी अगर आपने कुछ नहीं करना, किसी का सीमेंट पड़ा है, 10 बोरी सीमेंट पड़ा है, आपको थोड़े से उसके साथ खून लगा है, ठीक है, जाइए पानी गिरा दीजिए, बाल्टी लीजिए, पानी गिरा दीजिए, उसका सारा सीमेंट खराब देगा। 400 रुपए की बोरी है तो 10 बोरी 4000 रुपए होगी, 4000 का नुकसान कर दिया आपने उसका, लेकिन करना नहीं है। सीमेंट क्यों बोला मैंने, क्योंकि सीमेंट टाइट बना दिया आपने, सीमेंट को हार्ड बना दिया, सीमेंट टाइट बना दिया। जब भी आयरन को हम अचानक से पानी में डाल देते हैं ना, तो वो हमारे पास सीमेंट टाइट बनाता है। जब आयरन हमारे पास कार्बन मिक्स है और उसको ठंडा करेंगे, और कार्बन परसेंटेज भी मैटर करेगी, कार्बन परसेंटेज भी मैटर करेगी, और उसको ठंडा करने की प्रोसेस भी एयर में आराम से ठंडा करते हो तो उसमें हमारे पास परलाइट और फेराइट बनता है। लेकिन अचानक से क्वेंच कर देते हो तो उसके कारण सीमेंट टाइट बन जाता है, सीमेंट टाइट बन जाता है। और इन दोनों का मिक्सअप अगर आ जाए हमारे पास तो उसको लेडोराइट कह देते हैं, लेडोराइट कहते हैं। ये बीटेक में या एमटेक में हम इसके अंदर घुसते हैं आयरन कार्बन डायग्राम के, अभी हमें इतनी बहुत ज्यादा टेंशन लेने की जरूरत नहीं है, ठीक है। जो भी आपको जरूरत होगी, जो भी होगी वो मैं आपको करवा दूंगा। और इसमें बड़ा प्रॉब्लम है, मक्खी आगे बैठी, मक्खी नहीं मूव कर दिया इसको, मैं सोच रहा हूं इसको कौन मूव कर रहा है, वो मक्खी आगे बैठी, मक्खी टच करने लगी इसे, बताओ, है ना। एसी मतलब एसी लगाना 0.3%, ये आपको नोट करना है। 2.06, अब ये जो 2.06 है यहाँ पे मैं आपको बना देता हूँ, यहाँ पे ये वाला पॉइंट, यहाँ पे छोटा सा लाइन लगा देते हैं हम यहाँ पे। तो ये क्या है, 2.06% कार्बन इसमें होगा, वो हम रेडी है। दुनिया में जाओगे मतलब इतनी बात क्या करना है, जरूरत नहीं है, लेकिन नोट्स का टेंशन कर दो, मेरी वीडियो को शेयर कर दो, वो कि आपको ये वीडियो अच्छी लगी। हेलो दोस्तों, तो आज हम एक करने वाले हैं ट्रिक टू रिमेंबर रिएक्शंस इन आयरन कार्बन डायग्राम। तो आयरन कार्बन डायग्राम में 3 रिएक्शंस होती हैं, तो मेरे जैसे कुछ स्टूडेंट हैं जो भूल जाते हैं बार बार, तो उनके लिए मैंने एक ट्रिक बनाई है ताकि हम उसको याद कर सकें। देखिए आयरन कार्बन डायग्राम हमारे पास ये है, उसमें 3 रिएक्शन कौन सी होती हैं। 3 रिएक्शन होती है, पहली होती है हमारा पैरिटिक, दूसरी होती है टेक्टोइड और तीसरी होती है टेक्टिक। 3 रिएक्शन होती है, ओके। तो ये 3 रिएक्शंस क्यों होती हैं, कैसे होती है, इसके लिए मैंने वीडियो ऑलरेडी बनाई है, वो ऊपर लिंक दे रहा हूं, अगर वो देखेंगे तो वो देखिए। अब समझेंगे क्या ट्रिक, ताकि इनको याद कर सकें। तो पहले तो आपको बता दूं कि ये जो तीनों रिएक्शंस होती हैं वो कहां-कहां होती हैं। एक जो मेरे पास पैरिटिक है, अगर हम पैरिटिक देखें कि कहां पे होती है, तो वहां यहां पे होती है, यहां पे देखिए, यहां पे जो एरो लगा रहा हूं ना, ये वाली पॉइंट है जो ये वाला, तो यहां पे होती है पैरिटिक। और दूसरी होती है मेरे पास कौन सी, मेरे पास होती है यूटेक्टोइड, वो होती है ये यहां पे इस पॉइंट पे होती है यूटेक्टोइड। और तीसरी हमारे पास है जो कि इस पॉइंट पे होती है, और इस पॉइंट पे होती है यूटेक्टिक, तो ये होती है यूटेक्टिक यहां पे, ठीक है। तो उसकी डिटेल आप देख सकते हैं। अभी हम समझेंगे कि इसको याद कैसे रखना है, क्योंकि इसमें याद क्या रखना है, एक तो याद रखना है कि टेंपरेचर किस टेंपरेचर पे हो रही लिए ये रिएक्शन, और दूसरा इसमें कार्बन परसेंटेज क्या होती है, ठीक है, और इससे हमें मिलेगा क्या। ओके, तो सबसे पहले देखते हैं कि हम पेरियोडिक के बारे में देखते हैं कि इसमें क्या होता है। तो इसमें कहानी एक जोड़ी है, मैंने उसको आपने याद करना है कि हमारे पास देखिए एक परी है, पेरियोडिक से हमने परी और कार्बन बनता है, जब हम उसको ठंडा करते हैं वो क्या बनता है, ऑस्टेनाइट, ठीक है, उस स्टोरी से आपको समझ आ जाएगा। नेक्स्ट में अब देखिए आपने इस परी को तंग किया, अब परी के घर वाले भी तो आएंगे ना, तो अब उसके भाई और बाप आने वाला है। अब नेक्स्ट आता है हमारे पास यूट्रैक्टॉइड। तो यूट्रैक्टॉइड आपको कौन याद कराएंगे, वाइड। तो ये कह रहा है हमारे टेम्परेचर बना दे, यहाँ पे होती है। तो ये जो पॉइंट है, ये पॉइंट जो होता है वो 727 डिग्री सेंटीग्रेड पे, कहीं पे 723 डिग्री सेंटीग्रेड भी है, कुछ बुक इसे 727 भी लिखती हैं। तो ये हमारे पास 723 डिग्री पे और 727 इसके अराउंड है। तो इस पे टेम्परेचर पे, और यहाँ पे जो हमारे पास कार्बन परसेंटेज है वो है 0.8, ठीक है, यहाँ पे होता है। और ये अगर हम इसको ठंडा करते हैं तो ये क्या बनाता है, फेराइट और परलाइट, ठीक है, समझ आ गया। अब तीसरी बार आती है उसके बाप की। तो अब हमें यूटेक्टिक और 40 डिग्री सेंटीग्रेड पे, 1147 डिग्री सेंटीग्रेड पे होती है, ठीक है, इसी को समझ सकते हैं। और ये रिएक्शन और कितने कार्बन परसेंटेज पे, 4.3, उनके घर के बाहर लेबोरेटरी 4.3 कार्बन परसेंटेज है उसमें। और ये क्या हमें देता है, वो देता है पेरोलाइट और लेडब्राइट, ठीक है। अब एक चीज देखें, इन सब पॉइंट में एक वर्ड आता है हाइपो और हाइपर, आपने सिर्फ इतना याद करना है, ठीक है, हाइपर यूटेक्टिक।
Hi students. So today we are going to discuss TTT diagram. So I'm Kakala Krishna Kishore, professor in mechanics. Why is available, CCT diagram is available. So try to understand the basic information of a TTT diagram. So we are going to discuss in detail about TTT diagram in this session. Now let me discuss. See, the first point is what are the various transformation diagrams here. See, TTT diagram is a transformation diagram. So in general, there exist two transformation diagrams. That is one, these diagrams. Why these diagrams are meant for? Whatever the transformation diagrams are available, those transformation diagrams are helpful in selecting the optimum steel and the processing route. See, this is the main point here. Whatever the properties that you want to get for any material, if you want to get any say good material or the good taste, first of all you have to make the optimum property. It means you are going to see the optimum properties in any material before going to select. So that means you have to select or you have to see the transformation phase of that particular diagram or particular material. After seeing the material transformation diagram, then you can have some decision. It is helpful in selecting the optimum steel and processing route to achieve a given set of properties. Whatever the properties that you want to achieve, those properties, check whether those properties are existed or not. So all these things are available in transformation. The name itself is saying that it is a transformation diagram, one phase to another phase. We are going to see in detail. The first transformation that we are going to discuss in this session is time temperature transformation diagram, TTT, which is represented as a TTT. First T stands for time, second T stands for temperature, third T stands for transformation. Time temperature transformation diagram. Another diagram is also available. There is a transformation diagram which is represented as a continuous cooling transformation. We will discuss in next coming sessions. Now, in this session, that is in this video, we are going to discuss the diagram, and it is also represented as isothermal transformation diagram. Isothermal transformation means whatever the transformation that is going to happen can be temperature at some particular time. What is the structure of a material? That means the temperature, that is at that temperature at that time. What is the transformation? What is the phase? So all these details we can see in this diagram, and it is a graph is selected are more important forms of the iron alloy, so that we can see clearly in this diagram. Okay, now TTT diagram, this diagram also gives the temperature at which such a transformation takes place. So as I said now, so whatever the transformation is lying the y-axis here, y-axis represents the temperature. Here it is shown in degree centigrade, and the x-axis represents the time. Now, three lines you are seeing. First line, first one. Second one is a dotted line. Second, that cannot be called as a line. It is a curve. And third one is another curved line here. So these three lines represent the transformation lines. The first one represents the transformation beginning. This second line represents the after 50% transformation. The third one represents after the transformation ends. Now, and the left extreme position of the transformation beginning line is represented as a nose. These are the main points in DGT diagram. And above you can see the red line here. Above this gamma is existed, and gamma is going to be transformed. That is below this line, gamma is not going to be existed here. And below this temperature, that is below 700 or 723 degrees centigrade, gamma is not going to be existed, and we will get the different forms of arsenide, maybe pellet, maybe pyrite, or maybe any other thing here. If you observe the right extreme portions are different forms of the baryte. Cores depends on the cooling rate, depends on the temperature. It may be formed as a cores. At higher temperature, it is formed cores, perlite, fine perlite. Upper and here, after this temperature, whatever the formation is available, that is baryte, and this is called as a lower baryte. Baryte is going to be formed at this temperature, around this temperature, 400 to 500 or 300 to 500. At some uptime, that is at maximum time, the baryte is going to be formed. And if you observe here, some line is represented as a M here. Yes, M stands for martensite starting temperature. So that means here at around 200 degrees centigrade, martensite is going to be start. So this line stands for martensite starting temperature, and this is after 50% of the martensite is going to be formed, and this is martensite almost end temperature. Here, whatever the formation, that is the material that you are going to see at this temperature is martensite only. See, this is somewhat different from iron carbon diagram. The main features are this TTT diagram consists of three lines. First line is a transformation beginning, 50% transformation line, and a transformation ending line. The right portion of the transformation, that is TTT diagram, consists of perlite and baryte. At upper temperature, the perlite is existed. At lower temperatures, the baryte is existed. And at extreme lower temperature, the martensite existed due to the rapid cooling. This is due to rapid cooling. We will discuss those things also. First, see the figure. And the left extreme position of the transformation beginning curve, you can say that it is a curve. This curve is represented as a nose. That is a left extreme position. This point is represented as a nose point of TTT diagram. And one more point I want to discuss here. These curves will move to left or right. It depends on the percentage of carbon. That is, if it is a electric steel, one type of curve, that is, it may be moved left or it may be moved right. Depends on completely. It depends on the carbon percentage. Depends on the percentage. These transformation will change from left to right here. Okay. Now this is a TTT diagram. Now let us discuss salient features here. And before going to discuss the salient features, so what are the things you have seen in TTT diagram? That is below austenite. That is below A1 means below the top line. You can see this is A1 here. Below this line, even though the austenite is available, austenite is completely unstable. So that means austenite is not going to be existed below this red line. So that's why below A1, austenite is unstable. It can transform into maybe perlite or baryte or martensite. It has shown clearly that is in the picture. Below A1, there is no more austenite. And what are the phases they are formed here? These phases are formed during cooling. Depends on time and temperature. If it is a slow cooling, you will get perlite. If it is a medium cooling, you will get baryte. If it is a rapid cooling, that means a faster cooling, you will get martensite. So these are the three different structures are going to be formed. Depends on the rate of cooling. So that's why here it is mentioned formed during cooling depends on the time and temperature. Up to what time you are keeping the material at the temperature. That is also important for transformation. And the main point here is what are the diagram that you have seen? This diagram shows the time required for transformation. How much time is required for transformation? So is it a 1 hour or is it a 2 hours or is it 1,000 hours or whatever? So it will show how much clearly from this situation. Time required the transformation starting, and the blue line indicates the transformation ending line. And if you find any gap here, so that means the carbon percentage increases. If the carbon percentage is less, this nose point will close to the left extreme line. If the carbon percentage increases, this nose point will move to the right extreme position. So it depends. The transformation beginning is completely depends on the carbon percentage, whether it is going to be left or whether it's going to be right. You can see here at this portion, the blue line. You see above this line, austenite is stable, but after this, austenite is not stable. Austenite is going to be converted as a perlite or baryte or martensite here. You can see the growth of baryte here after the perlite is completed. So initially it is represented as a feathery baryte, or after that acicular baryte here like this. The formation of the baryte is like this. And here austenite is completely unstable. Austenite is not going to be existed. And after that, at bottom temperature around 200 degrees centigrade, the martensite starts. MS stands for martensite starts. This is a martensite starting temperature. Below this, austenite and martensite. So that means both the structures are going to be existed. Now, after completion of the austenite transformation, that means if the austenite is completely transformed into martensite, this is called as a martensite finishing temperature. So after it finishes, only martensite is existed. This is another form of the TTT diagram. Now you can see the structure of the perlite, and this is the structure of austenite here, and the various at slow cooling rates. Whatever the trajectory that here you have seen can pass through the perlite and baryte regions. Perlite, as I said earlier, the perlite is formed by slow cooling. baronite, baronite produced by rapid cooling. Martensite little bit faster compared to baronite. So perlite is a very slow cooling. Baronite is produced by rapid cooling, and the temperature is above ms. Above ms means martensite starting temperature. This part you have to remember. And the cooling is rapid enough. Austenite is transformed into martensite. That means if it is more rapid, then automatically the austenite is completely transformed into martensite. What are the transformation? As I said earlier, ms means martensite starting and mf means martensite finishing temperature. If cooling is stopped at the temperature between ms and mf, it will transform into martensite and baronite. So these are the salient features here. What are the transformations that we have discussed now? It indicates the amount of transformation. It indicates the austenite transformation held at different temperatures. So that's why we can say that we will get a large number of data. But if you want to get a large number of data, we have to conduct a large number of experiments. So this is briefing about the TTT diagram, time temperature transformation diagram. I hope you have understood the time temperature transformation diagram. In next coming sessions, we'll discuss some more videos. This is all about the TTT diagram. I am Kakala Krishna Kishore signing off. Thank you, and all. Hi students. Today we are going to discuss the CCD diagram and the various features of CCD diagram. I am Kakala Krishna Kishore, professor in mechanical engineering. So today we will discuss the various features, the salient features of a CCD diagram in brief. Now, let me discuss the details of CCT diagram. So exactly what is a CCT diagram here? Now, the CCT diagram means a continuous cooling transformation. It is a transformation diagram. It is very clear. But what is the difference between this diagram and the earlier diagrams? Earlier diagrams means so many transformation diagrams are available, especially two main transformation diagrams are available. This diagram is meant for, there is a CCT, which is represented as a CCT. CCT means continuous. C stands for continuous. Second C stands for cooling, and T stands for transformation. Continuous cooling transformation phase diagram is often used when heat treating the steel. So that means whenever you are giving heat treatment to the steel, automatically we can say that CCT diagram is required for that. So heat treating, as already you know that heat treating is meant to increase the strength of the material or to decrease if any impurities are available, if any residual stresses are available, we can easily remove with the help of heat treating to the steel. So steel is a ductile material in which so many properties are included. So that's why you must have some clear information for steel. So that's why this CCT diagram helps to identify the properties of the steel at various cooling transformations. So that means at a continuous cooling transformation. So the earlier diagram, suppose if you observe the TTT diagram, time temperature transformation diagram, so that transformation diagram, the information will get at constant temperature. But here the information is we will get the different phases, the different transformations with continuous cooling. So that is the main difference between TTT and CCT phase diagram. Now, as I said, these diagrams are useful to represent the which types of phase changes. What is the phase change existed will occur in a material when it is cooled at different rates. So that means here at different cooling rates, what is the phase of the material? That information we will get clearly from CCT diagram, continuous cooling transformation diagram. See, let me brief the transformation diagrams. What are the transformation diagrams existed and what is mean by transformation diagram? See, in general, there are two main transformations. As I said earlier, there are two main types of transformation diagrams that are helpful in selecting the optimum steel. See, as I said earlier, whatever the transformation diagram that you are going to draw, that you are going to only, and the process, the we're going to take before sample continuous. So if you take this sample, that is carbon percentage is less than 2% here. So that means that are going to be formed at different cooling rates. So these temperatures, 1200 degrees centigrade in thermomechanical simulator. You can take any other good simulator, but this is the main best simulator, thermomechanical simulator, until it reaches below, that is the CC cooling rate here. What is the suppose and here the main property? What is the physical property that is normally measured? It determines by measuring magnetic permeability and a specific volume during continuous cooling. See, that means we may have some doubt that how that is taking to show the image in coming slide. Let me the production continuous cooling transformation diagram, and here the high temperature means we can take the less time. So it depends on the temperature, the cooling rate or the time to take this diagram, time to draw this diagram is going to be reduced. It depends on the temperature, and if you don't hold at one temperature and allow time to change, so that means what do you mean by continuous cooling here? We are saying we are utilizing a continuous word here, continuous cooling. The main intention of this diagram is you are not supposed to hold the temperature. So that means you are not going to hold the temperature. How you can do that? If you don't hold at one temperature, if one temperature is not held, automatically you are in and allow time to change. So that means when the time continuous diagram is different from TTT diagram. In TTT diagram, it is a point I want to explain. These CCT diagram, that is continuous cooling transformation diagrams, are different from one material to another material. You cannot say that for all the materials the continuous cooling transformation is same. No, these diagrams are different from one material to another material. That means even if the composition changes, suppose say carbon percentage, steel means different carbon percentages are lines rates of the particular material, whatever the material that you have taken to draw this diagram. And the CCT diagram, again on y-axis it is the temperature, and on x-axis we have denoted time in seconds. Temperature here we have noted in degrees centigrade. And here also the same points almost, but here it is showing the continuous cooling transformation. In the TTT diagram, the main difference is it is showing the same materials, but it is due to the constant temperature. But here the continuous cooling transformation, and the begin 50% transformation and transformation. Here also you are seeing the three red lines here. The first row line represents the faster cooling. So that means the time is very less. If you cool the in faster rate, what are the changes existed? See, if you cool the material in a faster manner, you can have the martensite structure, a destructive structure. If you observe the martensite structure under microscope, you can see a pile of straw type of structure. It is a disturbed or destructive structure. So that means if your straws are at one stage, a pile of straw. So if you saw that type of structure, then we can say that it is a martensite structure. Martensite is going to be formed due to rapid cooling. This first line indicates faster cooling, and this faster cooling, due to this fast cool, the martensite is going to be formed. Now, coming then, it is suppose if you represent that as a moderate cool, then you will get the bainite structure, almost the bainite structure here. If you cool the material, the same material here, the material is not going to be changed. The material is same, the sample is same, the composition is same. The only change is the cooling rates. If you cool faster rate, you will get martensite structure, a pile of straw type of structure, destructive structure. If you cool at medium rates, that is a moderate cool, then you will get the bainite structure. So this is the bainite. So this structure, or this, the strength of this bainite is in between martensite and perlite. Perlite is a very, very soft structure. Martensite is a very, very hard structure. In between perlite and bainite, that is sorry, martensite, the bainite structure is available, and it is medium soft. And if you cool, now observe the third line here. If you observe the third line, this is by slow cooling. Obviously, by slow cooling, you will get the very, very fine structure, that is very, very soft structure, which is represented as a perlite. In general, it is a ferrite structure. So here, the ferrite structure, if you observe under microscope, you will get a fingerprint type of structure. If you observe a fingerprint structure, so you can say that the is transformation. See, transformation is happened, that is due to the austenite only. Okay, and that is transformed. So this is the information from CCT diagram. So this is another representation of the same figure. Here is the austenite is transformed. See, whenever transformation is happened, that is due to the austenite only. Okay, and the transformation, see, transformation is not going to be happened if the austenite is reaches. That means there is a CCT diagram. Whatever the CCT diagram that you have seen now, this diagram represents completely depends. So here, on the composition of the steel, as I said earlier, it completely depends on the austenite. Whatever structure is going to be different, and the hardness is going to be different. Extent of austenite homogenizing. Homogenizing means keeping the austenite at some temperature for a longer period of time. See, this is also important. And whatever the transformation is happened, there is a martensite or bainite or perlite, that completely depends on these. There is austenite grain size, or the nature of cooling, or the composition of steel, and as well as austenitic temperature and time. And the next feature is whatever the continuous cooling that you are going to form here. This constant temperature. Suppose if it is a TT diagram, it depends on the constant temperature. And these two are completely different diagrams. CCT and TTT diagrams. You can get the more relevant information. Why we are going for CCT diagrams? If already TTT diagram is available, we can get more relevant information obtained from CCT diagram. So that's why we are going to observe the continuous cooling transformation diagrams to analyze the various alloys of the steel. So that's why this diagram is very helpful in doing research in steels and in understanding the steel. So this is all about continuous. So thank you, one and all. Hi students. Today we are going to line is represented as M. Yes, MS stands for martensite starting temperature. So that means here at around 200 degrees centigrade, martensite is going to be start. So this line stands for martensite starting temperature, and this is after 50% of the martensite is going to be formed, and this is martensite almost end temperature. Here, whatever the formation, there is a material that you are going to see at this temperature is martensite only. See, this is somewhat different from iron copper diagram. The main features are this TTT diagram consists of three lines. First line is a transformation beginning, 50% transformation line, and a transformation ending line. The right portion of the transformation, that is TTT and ending position, this point are right. It the top line not going to be existed below this red line. So that's why below A1, austenite is unstable. It can transform into maybe perlite or bainite, or they are formed cooling structures of time that you are using 1,000 hours or whatever. So it will show how much time is required to form the bainite. Transformation. It is just showing only some few salient points of a TTT diagram. This is also TTT diagram only. The red line indicates the transformation starting, and the blue line indicates the transformation ending line. And if you find any gap here, so that means the carbon percentage increases. If the carbon percentage is less, this nose point will close to the left extreme line. If the carbon percentage increases, this nose point will move to the right extreme position. So it will be complete bainite that is and rapid cooling. Martensite little bit faster compared to bainite. So perlite is a very, very slow cooling. Bainite is produced by rapid cooling, and the temperature is above MS. Above austenite is transformed into martensite. That means early M that we have decided we will get exactly carbon phase diagram is going to be
If there's one material that defines
This video is brought to you by Skillshare. Get 3 months of learning for just 90 from iron urban industrialization. It forms the backbone of how the refining process of iron determines whether the resulting material will be iron or steel, and how the exact percentage of carbon present in the material has dramatic results on the final material properties, and how the production methods to one that is permeated edition of one muching tools for their communities. So to learn more about this Steel's workshop to create my own knife from scratch. We started our forging process with round stock 1055 steel with 0.55% carbon content, and placed it in the forge and gradually shaped it with a power hammer to a rectangular bar that could be more precisely shaped into the shape of our blade using a 3-pound hammer that my wee arms struggled to swing, producing our blade blank that would be later grinded to its final shape. But before that could happen, we needed to perform some metallurgy wizardry through the heat treatment process. To drive home how important this step is, we tested 4 samples of the same material at different stages of the heat treatment process. The hammer blows, which it absorbed, which was ductile with a low yield. C was the weakest of the bunch. This was our sample before the heat treatment process, which you will quickly see was the weakest of the bunch. This is the normalized sample, which was ductile with a low yield stress. It took several hammer blows, which it absorbed through plastic deformation, not ideal characteristics for a sword or knife. Next, we tested our quench hardened sample, which is stupid and dangerous and should not be tried at home. This fractured explosively and tore a hole through Alex's reflector. Finally, we tested the tempered material, which absorbed every hammer blow with minimal plastic deformation and only broke when we cut a notch into the material to create a stress concentration point. This material is tough, capable of absorbing energy without deforming permanently, and hard, allowing it to resist damage to the cutting edge. It is the ideal material for a blade. If any of these terms confuse you, I created a property. Well, this is the magic of the how can the same steel alloy change so radically by simply applying heat? Well, this is the magic of the iron-carbon alloy. We can carefully control how the internal metallic crystal structure forms with heating and cooling cycles. First, let's see how adding carbon to the iron affects the crystalline structure, with an iron atom at each of the 8 corners and another in the center. Each crystal structure has a direction it most easily wants to deform, called a slip plane. For body-centered cubic, the slip plane occurs along this plane. Metals with body-centered cubic crystals like iron and tungsten tend to be harder and less malleable than metals with face-centered cubic crystals like aluminium, lead, and gold. When a metal is cooling, these crystals grow from individual nucleation points and form grains where each grain has the same orientation of slip plane, but neighboring grains may not slip, but this grain slip plane is at a different angle, so that force needs to be greater in order to cause deformation. It's like trying to push a train down a railway track by pushing on its side. It's not going to go anywhere easily. So smaller and more numerous grains results in a stronger material. Pure iron tends to always have the same crystal structure as it cools, and its crystal structure doesn't change meaningfully with heat treatment. This is where alloying with carbon comes in. To explore this, let's look at our phase diagram for carbon steel. On this diagram, we have our carbon crystal or iron, which as we explained earlier forms only one crystal structure called ferrite. And more future, we started to transform into a new crystal structure called austenite state. Austenite's primary difference to ferrite is that it forms that face-centered cubic crystal structure that we saw earlier, while ferrite is body-centered cubic. And while this packing pattern is denser than body-centered cubic, it does open up spaces in the crystal structure that interstitial carbon atoms, which are smaller than iron, can snugly fit, allowing austenite to have a higher solubility to carbon over ferrite. Using all this information, let's take our 1055 steel with 0.55% carbon content and see how it transforms from the start of our heat treatment cycle to the end. The first step is called normalization. Normalization's primary function is to relieve internal stresses and strains that form during the forging process and return the material to its original crystal structure before forging began. It's effectively a reset button for the steel and creates a nice even grain size and distribution, increasing its strength. Here we place the knife inside a steel tube to prevent the metal from receiving heat directly from the flame, but instead a more even radiative heat from the tube. Once it reaches this transition temperature, we let it soak to give the crystal structure time to settle. The next step in normalization is to allow the steel to slowly air cool. What happens now depends on the carbon content. If we take a 0.8% carbon steel, no, hang on, we're definitely going to need a bigger graph for this. Okay, if we take a 0.8% carbon steel and cool it through the transitional temperature, the austenite and the interstitial carbon will slowly transform to a mixture of ferrite and cementite, which takes this laminar structure called perlite. Perlite only forms at a 0.8% carbon solution. Now if we take a 0.2% steel and slowly cool it to its first transitional temperature here, where ferrite first begins to form. Ferrite is pure iron, so as it forms, the carbon percentage begins to rise. This will continue to happen until the remaining austenite has a carbon percentage of 0.8% and will then form perlite from this point on. This forms a crystal structure dominated by ferrite, showing here as a lighter colour, surrounded by the darker perlite. Comparing these microstructures to another two, we can see the effect carbon has on the microstructure. Here we have pure iron with 100% ferrite, showing us the light colour. You can even see the grain boundaries. This is 0.5% carbon steel, similar to ours, where a very small amount of ferrite formed before reaching the point of perlite formation, and this is 0.8% carbon steel, where the entire structure is perlite, with our previous example showing perlite under 500 times magnification, where you can readily see that laminar structure. How perlite strengthens steel is not well understood. It has little effect on the steel's stiffness, but increasing the perlite content has a dramatic effect on the material's yield point, making it much more capable of absorbing energy without permanently deforming. But we can increase the material's stiffness and hardness with our next step. If we heat the metal back up to form austenite once again, but this time instead of letting it cool slowly, we rapidly cool it in oil while casually burning your arm hair off and barely flinching. The carbon atoms that spread out throughout the hot austenite structure cannot diffuse out of the crystal lattice to form cementite, and instead get stuck in solution, creating a new crystal structure called martensite. This crystal structure has a huge arm hair. This time, instead of letting it cool slowly, we rapidly cool it in oil while casually burning your arm hair off and barely flinching. The carbon atoms that spread out throughout the hot austenite structure cannot diffuse out of the crystal lattice to form cementite, and instead get stuck in solution, creating a new crystal structure called martensite. This crystal structure has a huge amount of internal stretching, in part because the carbon trapped within the crystal structure causes the crystal lattice to deform, but also because during the rapid cooling, the surface cooled much faster than the internal material. This causes internal tension in the material. These internal strains make it harder for additional deformation to occur, but this does not make the material stronger. It simply means that it will not stretch and bend before breaking. And when it finally does fracture, all of this internal tension is suddenly released in an explosive expansion. If you've watched Smarter Everyday's video on the St. Rupert's drop, you'll have seen this principle demonstrated in incredible slow motion. This material property is called hardness, and we want our cutting edge to be hard to resist damage when cutting. But we do not want our entire blade to be hard, as it will not be able to absorb a lot of energy. It needs to be able to dissipate some of that energy through heat and deformation. This is where the final step of the process comes in, called tempering. Tempering raises the temperature enough to allow the carbon trapped in solution to escape. We just use an oven set at 200 degrees. The carbon then coalesces to form cementite once again, but instead of forming perlite like before, it gathers in globules surrounded by ferrite. Tempering also relieves some of that internal tension caused by the rapid cooling. This reduces the hardness but increases toughness. This produces a material that has the perfect balance of characteristics between the normalized material and the hardened material. It is ductile enough to absorb hammer blows without shattering, but strong enough to not permanently deform, and with enough hardness to ensure it doesn't gather damage on the cutting edge. This process gave our steel the perfect material properties, and a lot of that is thanks to the quality of the steel we started off with. Learning these skills with Alec was a lot of fun, and I highly recommend you check out his channel. His incredible attitude to work really inspired me to start learning some new hands-on skills this year, and I'm hoping to start that off by learning how to program and create robotics with an Arduino. This course I found on Skills Game and Curve 9th of January. Those right sure if you
If there's one material for affordability, but from something unique, its ability to be transformed through heat treatment. Take these three steel parts. The first is soft and ductile, the second is very hard and brittle, and the third is strong and tough, but they all have the exact same chemical composition. The only difference is they've been heat treated in different ways. This ability to control and fine-tune the properties of the material through precise heating and cooling really is the superpower of steel. So let's see how it works. First, the ingredients. Steel is an alloy of iron and carbon and usually a few other elements in small proportions. Steels are classified based on carbon content, as low carbon, medium carbon, and high carbon steels. Anything beyond that, above 2.1% carbon, is called cast iron. If a steel contains a significant amount of alloying elements, above around 1%, it's called an alloy steel. Otherwise, it's a plain carbon steel. To understand how heat treatment can transform the properties of these materials and the effect different carbon concentrations can have, we first need to look at the main ingredient, iron, to see how it behaves at different temperatures. Pure iron goes through several changes as it's heated. At room temperature, the iron this is in a different atomic arrangement and packed more closely and efficiently. Let's visualize the phase transformations of iron on a graph. The ferrite to austenite transformation happens at 900 degrees, called allotropes of iron, and for convenience, a Greek letter is assigned to each phases within the alloys. The amount of carbon in the alloy affects the transformation temperatures, but it also introduces new phases. The structure of ferrite can only accommodate a tiny amount of carbon. It has a maximum solubility of 0.02% carbon by weight at 723 degrees, which is around 1 carbon atom for every 1,000 iron atoms, and it's even less than that at lower temperatures. If the alloy composition contains more carbon than the ferrite can handle, the excess carbon atoms have to go somewhere. So a new phase, called cementite, forms alongside the ferrite. Cementite is a hard, brittle compound, made up of 1 carbon atom for every 3 iron atoms. Austenite can hold a much larger amount of carbon than ferrite, from 0.8% at 723 degrees to 2.1% at 1,147 degrees, which is roughly 1 carbon atom for every 10 iron atoms. If more carbon is added, we obtain a 2-phase material with austenite and cementite phases. There are several other possible phase combinations depending on the temperature and the amount of carbon. The phase diagram tells you which microstructures form at different temperatures and for different carbon concentrations, and as we'll see later on, this is the key to understanding how heat treatment works. For an alloy containing 0.8% carbon, the structure remains austenite while cooling until it reaches 723 degrees. At this temperature, the austenite undergoes a transformation from an FCC to a BCC structure, and the excess carbon the new BCC structure can't contain combines with iron atoms to form cementite. These two phases form a distinctive microstructure consisting of alternating layers of ferrite and cementite, which is called pearlite. This composition is a special case because the austenite transforms entirely and simultaneously into ferrite and cementite, producing only pearlite. The point on the graph at which this happens is called the eutectoid point, and steel with the corresponding 0.8% carbon composition is called eutectoid steel. In hypo-eutectoid steels, those containing less carbon than the eutectoid composition, some ferrite forms before the eutectoid temperature is reached. On further cooling, the remaining austenite transforms into pearlite. The final microstructure ends up being a mix of pro-eutectoid ferrite and pearlite. In hyper-eutectoid steels, cementite forms first, as the austenite cools. At the eutectoid temperature, the remaining austenite transforms into pearlite, so the final microstructure is a mix of pro-eutectoid cementite and pearlite. All of these transformations rely on diffusion, the movement of carbon and iron atoms through the lattice to form new layers. But it can take minutes, hours, or even days for austenite to fully transform into ferrite, determined through testing. A small sample is heated until it's fully austenite, then rapidly cooled to a target temperature and held there for a set amount of time. After this hold, the sample is rapidly cooled to room temperature to interrupt the transformation, and the microstructure can be examined to get an idea of how much of the austenite has turned into ferrite and cementite. By repeating this test for different temperatures and holding times, you can start to map out the relationship between time, temperature, and the phases that form in a given steel. This is called a time-temperature transformation, or TTT diagram. The dashed line at the top of the diagram marks the equilibrium transformation temperature. At temperatures below this line, austenite is unstable. Given enough time, it will eventually transform into ferrite and cementite. The diagram shows us how long this transformation will take if the steel is cooled to and held at a constant temperature. If this eutectoid steel is cooled to and held at 500 degrees, for example, the diagram tells us the austenite will start transforming into ferrite and cementite in less than a second, and the transformation will complete after about 9 seconds, leaving no remaining austenite. The TTT diagram is where things get really interesting, because it's where we start to see non-equilibrium phases emerging, phases that play a central role in heat treatment. The most important of these is the martensite phase. It forms when austenites cool so rapidly the carbon atoms don't have time to diffuse out of the FCC structure to form cementite. The FCC lattice wants to transform to BCC, but can't because of the trapped carbon atoms, so it ends up distorting into a new, body-centered tetragonal structure instead, which is called martensite. The BCT lattice forms almost instantly, growing out from austenite grain boundaries, and propagating at close to the speed of sound. This happens so fast because the transformation from FCC to BCT is diffusionless. Unlike the other phase transformations we've seen, it happens without any long-range motion of the atoms. The result is a microstructure of long, thin plates of martensite slicing through the prior austenite grains, each plate being a region where the atoms have all displaced in the same direction to form the BCT lattice. The distorted lattice of martensite makes it an extremely hard and strong, but also very brittle material. This is due to the trapped carbon atoms, which strain the lattice, locking the structure in place and impeding the motion of dislocations. The steel's carbon content has a big impact here. More carbon means greater distortion of the lattice, which increases hardness and strength at the cost of increased brittleness. On the TTT diagram, martensite appears as a region stretching along the bottom of the graph. 3 horizontal lines mark the temperatures at which martensite formation starts, reaches 50% completion, and finishes. Because it's diffusionless, no time elapses before starting or completing the transformation. It happens immediately once the temperature drops below the martensite start line. If the steel is cooled to a temperature between the martensite start and finish lines, only part of the austenite transforms, leaving a mix of martensite and retained austenite. A whole range of other microstructures can be achieved by manipulating time and temperature. A key feature here is the inflection point of the TTT diagram, often called the nose of the diagram. It marks the shortest transformation time, the temperature at which austenite is least stable and begins to transform most rapidly. Above the nose, we get pearlite, the alternating layers of ferrite and cementite we saw on the iron-carbon phase diagram. At higher temperatures, the transformation proceeds more slowly, giving carbon atoms time to move over longer distances, resulting in a coarse pearlite microstructure with wider spacing between ferrite and cementite layers. At lower temperatures, carbon atoms have less time to diffuse, so the structure forms quickly as fine pearlite, with closely spaced layers. Fine pearlite is stronger than coarse pearlite, because the hard, brittle cementite layers are more closely spaced, creating effective barriers to the motion of dislocations. Below the nose, diffusion distances are even more restricted, which allows a different microstructure, bainite, to form. This is still a combination of ferrite and cementite, but with a much finer, more irregular mixture of the two phases. This gives bainite an excellent balance of strength and toughness, making it a target in some heat treatments. Upper bainite and lower bainite form at higher and lower temperatures within the bainite range, and have distinct microstructures. In practice, steels aren't usually cooled to a fixed temperature and held there. More often, they're cooled continuously down to room temperature. The phase transformations that occur with these more realistic cooling conditions are shown on a continuous cooling transformation, or CCT diagram. This is similar to the TTT diagram, except instead of holding the steel at a fixed temperature, the diagram is based on continuous cooling paths. Each of these curves represents a different linear cooling rate. Cool this 1080 steel from 800 degrees Celsius at a rate of 200 degrees per second, and you'll obtain martensite. At 50 degrees per second, you'll obtain a mixture of pearlite and martensite, and at 10 degrees per second, you'll get 100% pearlite. The CCT diagram shows how difficult it can be to obtain martensite. Plain carbon steels often require very high cooling rates to miss the nose of the curve and end up in the martensite region, rates that aren't achievable in practice. This is one of the main reasons alloying elements like nickel and manganese are added to steel. They shift the CCT curves to the right, so that martensite can be obtained at slower cooling rates. Unlike the TTT diagram, the CCT diagram doesn't show bainite in the area below the nose, because any cooling path that hits the nose will transform into pearlite, and pearlite can't transform into bainite without being reheated to austenite. This is another use of alloying elements. They can be added to delay pearlite transformation, which uncovers a bainite nose and allows bainitic steels to be obtained at certain cooling rates. It's this complex choreography between chemical composition, transformation kinetics, and the resulting microstructure that makes steels because any cooling path that hits the nose will transform into pearlite, and pearlite can't transform into bainite without being reheated to austenite. This is another use of alloying elements. They can be added to delay pearlite transformation, which uncovers a bainite nose and allows bainitic steels to be obtained at certain cooling rates. It's this complex choreography between chemical composition, transformation kinetics, and the resulting microstructure that makes steels such complex and fascinating materials. Now we can finally get to heat treatment, which is all about using careful heating and cooling fascinating materials 100 degrees continuous down to room temperature. completion, it happens immediately when site time and temperature. A key feature here is the perlite, the alternating layers of ferrite and cementite we saw on the iron-carbon phase diagram. At higher temperatures, the transformation proceeds more slowly, giving carbon atoms time to move over longer distances, resulting in a coarse pearlite microstructure with wider spacing between ferrite and cementite layers. At lower temperatures, carbon atoms have less time to diffuse, so the structure forms quickly as fine pearlite with closely spaced layers. Fine pearlite is stronger than coarse pearlite because the hard, brittle cementite layers are more closely spaced, creating effective barriers to the motion of dislocations. Below the nose, diffusion distances are even more restricted, which allows a different microstructure, bainite, to form. This is still a combination of ferrite and cementite, but with a much finer, more regular mixture of the two phases. This gives bainite an excellent balance of strength and toughness, making it a much finer BCT material of dislocation, which ends up to the FCC lattice wants to transform to BCC, which is called martensite, and propagating cool this 1080 diagram, except instead of holding the steel at a fixed temperature, the diagram is based on continuous cooling paths. Each of these curves represents a different linear cooling rate. Cool this 1080 steel from 800 degrees Celsius at a rate of 200 degrees per second, and you'll obtain martensite. At 50 degrees per second, you'll obtain a mixture of pearlite and require very high cooling rates to the nose of the curve and end up in the martensite region, rates that aren't achievable in practice. This is one of the main reasons alloying elements like nickel and manganese are added to steel. They shift the CCT curves to the right so that martensite can be end up in the martensite region. These are added to steel in practice. This is one of the main reasons alloying elements like nickel and manganese get to or improve material properties. 4 key heat treatment processes are annealing, normalizing, quenching, and tempering. Let's see how they work. Annealing is used to make steel soft, ductile, and easy to work with. It's often applied to steel parts after forging or casting to relieve stresses and make the part easy to machine. The process involves heating the steel into the austenite region, then cools and make the part ductile and easy to work with. Annealing is used to make steel soft, ductile, and easy to work with. It's often applied to steel parts after forging or casting to relieve stress and make the part easy to machine. The process involves heating the steel into the austenite region. Then cooling it very slowly inside the furnace. Because the cooling is so gradual, the carbon atoms have plenty of time to rearrange into the wide ferrite and cementite layers of coarse pearlite, which has low strength, but is very soft and ductile. Annealing is usually a preparation step before machining or other processing. Normalizing is similar to annealing. Both heat the steel into the austenite region, with normalizing using a slightly higher temperature. The main difference is the steel is cooled in air instead of slowly in the furnace. The higher temperature helps better eliminate irregular or patchy microstructure left over from previous processing steps like casting or rolling. And the faster cooling rate produces a fine pearlite structure that's stronger and harder than annealed steel, while still retaining useful ductility. The process normalizes the steel, resetting it to a uniform, fine microstructure with good strength and hardness. Quenching is a heat treatment process that involves very rapid cooling, usually by plunging the steel part into a bath of water. Quenching is a heat treatment process that involves very rapid cooling, usually by plunging the steel part into a bath of water, oil, or other medium, depending on the cooling rate required. The objective of this rapid cooling is to produce martensite. The quenched steel has high hardness and strength, but is far too brittle to be of use in most applications. Tempering is a follow-up process to quenching. The quenched martensite steel is reheated to temperatures between 200 and 600 degrees Celsius. Below the levels needed to transform the steel into austenite. It's held at this constant temperature for a defined time period, anywhere from a few minutes to several hours before cooling, usually in air. During this tempering process, excess carbon atoms trapped in the distorted, supersaturated martensite lattice diffuse out and combine to form extremely fine particles of cementite, allowing the BCT martensite lattice to relax back towards a BCC ferrite structure. The resulting microstructure is called tempered martensite. This transformation greatly improves the ductility and toughness of the quenched steel, while still retaining much of its strength and hardness, thanks to the finely dispersed cementite particles. Steel in this quenched and tempered condition is usually referred to as hardened steel. Quenching and tempering is used for critical parts that need high strength combined with toughness, like crankshafts, high-strength bolts, tools, or heavy-duty structural components. It needs sufficient carbon to be effective, though. In low-carbon steels, even if martensite forms during quenching, there's too little carbon to significantly distort the lattice, so these heat treatments produce little to no increase in strength and hardness. The objective of quenching is to cool the material fast enough that austenite turns into martensite through the entire cross-section of the material. This can be challenging with thick components, where the core of the material will take longer to cool than the surface, resulting in pearlite or bainite forming within the part instead of martensite. Hardenability is a parameter used to quantify a steel's ability to form martensite to a given depth during quenching. A steel with good hardenability will be able to form martensite more easily at slower cooling rates, and produce martensite all the way through thick sections. The Jominy end quench test is the standard method for measuring the hardenability of steel at a controlled cooling rate quenched end. Minimum hardness at the quenched end on the only in Martin before and applicate keep extraordinarily corroding steels, because low carbon steels don't contain enough carbon to develop sufficient hardness. Nitriding introducing a carbon rich and actually alter the surface of carbon of the component, followed by quenching to create a hard to intentionally create a hard outer layer, while directly heating the surface of carbon to develop sufficient hardness. For low carbon steels, case hardening techniques that actually alter the surface composition can be used instead. Carburizing involves heating the part in a carbon rich environment. Challenging with thick components, where the core of the material will take longer to cool than the surface, resulting in pearlite or bainite forming within the part instead of martensite. Hardenability is a parameter used to quantify a steel's ability to form martensite to a given depth during quenching. A steel with good hardenability will be able to form martensite more easily at slower cooling rates and produce martensite all the way through thick sections. The Jominy end quench test is the standard method for measuring the hardenability of steel. Steels. It involves heating a cylindrical steel sample that's 1 inch in diameter and 4 inches long. Until it's fully austenitic. One end of the sample is then quenched with a standardized water spray setup, creating a controlled cooling rate that decreases as you move up the sample. A flat is then ground along the length of the sample, and Rockwell hardness measurements are taken at regular intervals from the quenched end. The results are plotted as a Jominy hardness curve. Hardenability is mainly determined by composition. These different steel grades have very different curves. The maximum hardness at the quenched end on the left of the graph is governed by carbon content. The 1080 steel reaches a higher hardness at the quenched end than the 1040 steel because it contains more carbon. But the rate at which hardness decreases with distance from the quenched end is mainly influenced by alloying elements. These elements shift the TTT needed here, hardening, quenching, to create a hard, carbon steels, involves heating the part in a carbon-rich environment to increase surface carbon content, followed by quenching.
Must act damage. The combination of a hard surface and a soft interior is greatly valued in modern engineering because it can withstand very high stress and fatigue. They are properties that are useful in parts such as cam or ring gear, bearings or shafts, turbine applications, etc. The process used to achieve this is known as surface hardening. Therefore, surface hardening is defined as a process by which a metal is given a hard, wear-resistant surface while retaining a ductile but tougher interior. It is a method used to improve the wear resistance of metal parts without affecting the softer and tougher interior of the part. The surface hardening technique can be classified into two major categories. 1. Case hardening or diffusion method. 2. Selective surface hardening method. Case hardening. Case hardening, which is a surface hardening process by diffusion, involves the chemical modification of a surface. They are processes that change the surface chemical compositions. Case hardening methods include carburizing, nitriding, carbonate riding, and cyaniding. Carburizing. Carburizing is a surface voltage method used to improve the wear resistance of metal parts without affecting the softer and tougher interior of the part. The surface hardening technique can be classified into two major categories. 1. Case hardening or diffusion method. 2. Selective surface hardening method. Case hardening. Case hardening, which is a surface hardening process by diffusion, involves the chemical modification of a surface. They are processes that change the surface chemical compositions. Case hardening methods include carburizing, surface density on the surface, as the surface hardening, in plasma, sweet parts of nitride, high wear situations processed. The process, carbon and earth composite operation, has advanced a process of hardening that does not change the surface chemical composition. This can be achieved by localized heating and quenching, without any chemical modification of the surface. The more common methods of selective surface hardening currently used to harden the surface of steel include flame hardening and induction hardening. Flame hardening. Flame hardening is a process of Therefore, surface hardening is defined as a process by which a metal is, while the basic principle of carburizing has steels for such carbon is introduced in it riding and cyaniding. Carburizing. Carburizing is a surface hardening process in which carbon is introduced into the surface layer of steel. It is the oldest surface hardening method, in which steel is placed at a high temperature for several hours in a carbonaceous environment. Case hardness of carburized steel is primarily a function of carbon content. The steel is heated in contact with a substance that has a high carbon content at a high temperature, generally between 850 to 950 degrees Celsius, and held at that temperature for a suitable period. It is then quenched rapidly to produce a hardened surface layer or martensitich case, with good wear and fatigue resistance over a softer and tougher core. The depth of the carburized case depends on the carburizing time, the steel chemistry, and the available carbon at the surface. Most steels that are carburized are killed steels. Since the carburizing process does not harden the steel, but only increases the carbon content to a desired depth below the surface, the case and core have quite different hardenabilities. While the basic principle of carburizing has remained unchanged since it was first introduced, the methodology has gone through continuous evolution. Various techniques of carburizing have been developed to increase efficiency and reduce cost. In its earliest application, parts were simply placed in a suitable container and covered with a thick layer of carbon powder, pack carburizing. Although effective in introducing carbon, the pack carburizing method was exceedingly slow, and as the production demand grew, a new method using a gaseous atmosphere was developed. Despite the increased complexity, gas carburizing has become the most effective and widely used method for carburizing steel parts in high volume. To summarize, the carburizing method includes pack carburizing, gas carburizing, vacuum carburizing, liquid or salt bath carburizing. Nitriding. Nitriding is a surface hardening process that introduces nitrogen into the surface of steel at a temperature range of 500 to 550 degrees Celsius in its ferritic conditions. Nitriding is most effective for alloy steel which contains stable nitriding forming elements such as chromium, molybdenum, vanadium and tungsten. Because nitriding does not involve heating into the austenite phase with quenching to form martensite, nitrided components exhibit minimum distortion and excellent dimensional control. Nitriding time depends on steel composition and the depth of hardening desired. The process methods for nitriding include gas, liquid and plasma nitriding. Plasma nitriding, also known as the ion nitriding process, is a method of surface hardening using a glow discharge technology to introduce nitrogen into the surface of metal, which subsequently diffuses into the metal. In this process, the steep components to be nitrided act as cathode. The component is heated by an electrical heater to using a glow discharge nitriding, and the depth of hardened nitrided components effective for surface of steel rising. Nitriding. Nitriding is a surface hardening process that introduces nitrogen into the surface of steel at a temperature range of 500 to 550 degrees Celsius in its ferritic conditions. Nitriding is most effective for alloy steel which contains stable nitriding forming elements such as chromium, molybdenum, vanadium and tungsten. Because nitriding does not involve heating into the austenite phase with quenching to form martensite, nitrided components exhibit minimum distortion and excellent dimensional control. Nitriding time depends on steel composition and the depth of hardening desired. The process methods for nitriding include gas, liquid and plasma nitriding. Plasma nitriding, also known as the ion nitriding process, is a method of surface hardening using a glow discharge technology to introduce nitrogen into the surface of metal, which subsequently diffuses into the metal. In this process, the steep components to be nitrided act as cathode. The component is heated by an electrical heater to 600 degrees Celsius. This heating operation is followed by switching on the supply of a gas mixture of hydrogen and nitrogen at low pressure. Sufficiently high DC voltage, 500 to 1000 volts, is applied between the cathode components and anode to form plasma. Current flows between the two electrodes and the mixture of hydrogen and nitrogen gas gets ionized. The cathode component to be treated is subjected to this ionized discharge. The nitrogen ions that are formed bombard the surfaces of the component with considerable energy. Parts of the energy heat the cathode components and allow diffusion of nascent nitrogen inward from nitrides. The remaining parts of energy are used for displacing the secondary electrons from the cathode surface. The processing time for gas nitriding can be quite long. Plasma nitriding allows faster nitriding time, and the quickly attained surface saturation of the plasma process results in faster diffusion. Due to these improved capabilities, the plasma nitriding method has become increasingly popular. Carbonitriding. Carbonitriding is a surface hardening process by which carbon and nitrogen, via ammonia gas, permeate the surface layer of steel components. The process involves a temperature of around 850 degrees Celsius, followed by quenching in oil or gas solutions. The carbonate riding process combines simultaneously nitriding and carburizing, and while these two processes are distinguishable, they are not completely independent. The goal of the process is to introduce carbon and nitrogen into steel in its austenite condition, which becomes a martensite matrix microstructure after quenching. The diffused nitrogen has a stabilizing effect on austenite and lowers the critical quenching speed, and as a consequence, the hardenability of the steel. Carbonitriding is performed in a gas atmosphere furnace using a carburizing gas such as propane or methane, source of carbon, mixed with several volumes % of ammonia, source of nitrogen. The process is carried out at lower temperatures, and generally for shorter times than carburizing, and therefore the components are less prone to distortion. If there is too much nitrogen introduced to the steel, it can result in retained austenite, which is austenite that does not become a martensite microstructure after quenching. Successful completion of the carbonate riding process will grant the steel components a variety of beneficial properties, most notably increased wear resistance, and there are many different applications for carbonitrided parts in high wear situations such as gear teeth, bearings and tools. Cyaniding. Cyaniding is similar to carbonate riding in that the process involves both the diffusion of carbon and nitrogen into the surface layers of the steel. Cyaniding is carried out in a liquid bath of sodium cyanide. If the process is carried out in a gaseous atmosphere, it is called carbonate riding. In the cyaniding process, the part to be surface treated is immersed and heated in a liquid bath of sodium cyanide at 800 to 960 degrees Celsius, with the concentration varying between 25% and 90%, then quenched in brine, water or oil. In the process, the measured amount of air is passed through the molten bath. Sodium cyanide reacts with oxygen in the air and oxidizes. Carbon and nitrogen form in atomic form, diffuse into the steel and give a thin wear-resistant layer of the carbonitride phase. Salt bath composition may vary according to the temperature of the salt, the thickness of the case to be obtained, the type of steel to be heat treated, and the period of operations. This process is not suitable for surface hardening those parts which are subjected to shock, fatigue and impact, because nitrogen addition has adverse effects on such properties of steel. 2. Selective surface hardening method. Selective surface hardening is a process of hardening that does not change the surface chemical composition. This can be achieved by localized heating and quenching, without any chemical modification of the surface. The more common methods of selective surface hardening currently used to harden the surface of steel include flame hardening and induction hardening. Flame hardening. Flame hardening is a process of austenizing the surface of steel by heating it with an oxyacetylene or oxyhydrogen torch, and immediately quenching it with water or water-based polymer. The result is a hard surface layer of martensite over a softer interior core with a ferrite perlite structure. Flame hardening increases a steel component's malleability while hardening its surface. There is no change in composition, therefore the flame-hardened steel must have adequate carbon content for the desired surface hardness. Typically, flame-hardened steel is used in automotive equipment components like gears and blades, because of its high wear resistance. The disadvantage of flame hardening is the possibility of part distortion as a result of overheating. Induction hardening. Induction hardening is a complex combination of electromagnetic heat transfer and metallurgical phenomena that can perform uniform surface hardening and localized surface hardening on metal pieces. It is a method of quickly and selectively hardening the surface of a metal part. A high-frequency alternating current is generated in a copper tool electrode, primary coil, which is adapted to the shape of the workpiece to be hardened. This in turn leads to a constantly changing magnetic field around the electrode, which penetrates the adjacent workpiece and generates eddy currents due to the induction effects. These very large eddy currents of up to several thousand amperes per square millimeter lead to heating of the workpiece. The workpiece is then quenched in water, which transforms the structure to martensite, which is much harder. The depth of heating produced by induction is related to the frequency of the alternating current, power input time, part coupling and quench delay. The higher the frequency, the thinner or more shallow the heating. Therefore, deeper case depths and even thorough hardening are produced by using lower frequencies. Some of the benefits of induction hardening are faster process, energy efficiency, less distortion and small footprints. Its disadvantage is its high cost. Laser hardening. Laser hardening is a surface hardening process commonly used for complicated shapes or large objects because it allows for absolute control of the surface hardening and texture. This process is sometimes referred to as laser transformation hardening to differentiate it from laser surface melting phenomena. There is no chemistry change produced by the laser hardening method. The process, like induction and flame hardening, provide an effective technique to harden ferrous materials selectively. The process consists of the rapid heating of a material surface by laser beams, a short hold at the target temperature, and an intensive cooling due to the high thermal conductivity of the material, resulting in very fine martensitich microstructure, even in steels with relatively low hardenability. Laser hardening can be used to locally improve wear resistance and service life of parts for a wide variety of applications, from press-forming tools to oil drilling equipment. The technology is suitable for applications where minimal heat input into the surrounding material is critical. Electron beam hardening. Electron beam hardening, like laser hardening, is used to harden the surface of steels. Electron beam hardening uses a concentrated beam of high-velocity electrons as an energy source to heat a selected surface area of ferrous parts. Some advantages of surface hardening include improved surface wear resistance,
The development of composite super materials over the last few decades has completely transformed how some of the most advanced engineering problems out there can be solved. It's allowed the development of materials with unique thermal properties that can better handle the blistering temperatures of atmospheric re-entry, for example. And has pushed the limits of jet engine design through the use of lightweight fan blades that have carefully tailored mechanical properties. But what exactly are composite materials, and what makes them so special? Let's find out. A composite is really just any material made from two or more distinct constituent materials. They can be found in nature. Wood is just one example of a natural composite material. But they can also be engineered, where different materials are carefully combined to develop all sorts of incredible and exotic composites that have mechanical, electrical, thermal, or even magnetic properties that have been tailored to suit a specific application. In most composites, one material, called the dispersed phase, is contained within another, called the matrix phase. The ability to carefully select each phase to optimize the properties of the material for a specific application is what makes composites so powerful. The dispersed phase is usually what provides the desirable material properties, like high strength or improved ductility, and is usually either a ceramic or a metal. Composites are often categorized based on the form of the dispersed material. This is a particle-reinforced composite, but the matrix material is transferred between them. It holds everything together, and it protects the dispersed phase from the environment. Composites are also categorized based on the type of matrix material, which can be a polymer, a ceramic, or even a metal. a ceramic, or even a metal. Probably the most widely used composite materials in engineering applications are the fiber-reinforced polymer matrix composites. This category of composites includes glass-reinforced polymers, also called GRP or fiberglass, and carbon fiber-reinforced polymers, or CFRP. These composites usually have an epoxy matrix, which is a thermosetting polymer, and the dispersed material is glass or carbon fibers, which make up around 60% of the material by volume. The most basic form of fiber reinforcement is unidirectional tape, which has all of the fibers running in the same direction. The individual fibers are grouped together into bundles, which are held together with stitching or using a chemical binder. In the case of carbon fibers, these bundles are called tows. Each tow usually contains anywhere from 3,000 to 24,000 individual fibers. A typical fiber is around 10 microns in diameter, which is 10 times thinner than a human hair. Any fiber-reinforced material that has fibers all running in the same direction will be highly anisotropic. Its material properties will be different in different directions. If you apply a load along the axis of the fibers, load is changing. If you know that your material will be loaded mainly in one direction, you can orient the fibers to make it very strong in that particular direction. In pressure vessels, for example, fibers can be aligned mostly in the hoop direction, because the hoop stress is the largest stress when the vessel is pressurized. In most cases, though, you need good strength and stiffness in several directions at the same time. Reinforcement in the axial direction, either with axial or by stack or apply, and the stack is called the laminate. In this laminate, the 0-degree layer provides strength and stiffness in the axial direction. The 90-degree layer provides it in the correct orientations. The laminate can have very similar properties in all of the in-plane directions. This is called a quasi-isotropic laminate, which have fibers running in two different directions. There are hundreds of possible weave patterns. This is a plane weave, but a twill weave is more flexible and will conform more easily to a curved surface, for example. Weave patterns have good stiffness and strength along the two fiber axes, but they're weak at 45 degrees, so they should be layered in different orientations if quasi-isotropic properties are needed. Once the laminate structure has been defined, the different fiber layers need to be assembled and combined with the polymer matrix to create the final composite part. One way of doing this is the wet layup method, where fiber layers are built up in a mold, and the resin is applied to each layer using a roller or a brush. The number of plies and ply orientation are carefully selected to achieve the required properties. An alternative method involves the use of pre-preg, tapes or sheets of fibers that have been pre-impregnated in a partially cured epoxy resin, meaning they can be applied to the mold without needing and then be vacuum-bagged to ensure it conforms well with the thermal temperature. Unidirectional tape that has been impregnated with resin around a mandrel. Once complete, the mandrel can either be left in place or removed, and the structure is cured. Other methods like injection molding can be mechanical, which represents the stiffness, has a tensile strength of around 600 megapascals, and a Young's modulus similar to aluminum, although the exact proportion are stiff. These materials correspond to high modulus variants. We can also plot glass fiber reinforced polymers, which have lower stiffness but very good tensile strengths that are optimized for different applications when considering materials. Materials are why they're so commonly used in industries where weight reduction is critical, like aerospace, the automotive industry, and even in sports like cycling and sailing. Glass fiber reinforced composites have lower stiffness than CFRP, but excellent strength properties on a blade due to the small diameter is limited. The larger a fiber is, the more likely it is that it will contain more defects, and that the defects will be larger. But in the bundle of smaller fibers, stronger. Not only that, but in the bundle of smaller fibers, failure of a single fiber can occur without hugely increasing the load on the remaining fibers. And the smaller the fibers, the larger the surface area between the fibers and the matrix, which means better load transfer between the two. The result is that the strength of a fiber reinforced material increases significantly as the fiber diameter reduces. The main thing limiting the use of ever thinner fibers is manufacturing constraints for their good specific strength and specific stiffness. They have many other useful properties that provide advantages over traditional materials like steel and aluminum alloys, dynamic loads, and they from the environment, and have a dimension. The cost is to design with, and aluminum because they have high strength and stiffness for reinforced polymers alongside steel and an aluminum alloy. Fibers tend to be made from materials like glass and carbon because they have high strength and stiffness, but they're also very brittle. This means the resulting composite material is also quite brittle. CFRP in particular will fail at very low strains compared to steel and aluminum alloys. A well-known fiber reinforcement we haven't mentioned yet is Kevlar, a type of aramid fiber. Kevlar reinforced polymers are stiffer and stronger than GRP, more ductile than CFRP, and lighter than both. This makes them ideal materials for applications where excellent impact resistance is required, like in body armor. 100 or 200 composites can be silicon withstand temperatures upwards of 1000 degrees Celsius. Ceramics have other properties that make them use, plus they have high strength and high stiffness. Carbon has similar properties to these ceramics. With a melting point above 3000 degrees, it can handle extremely high temperatures. But all of these materials are very brittle. They fracture suddenly at very low strains. Significantly increased toughness. To see how this works, let's compare two ceramic materials, with and without fiber reinforcement. Both contain an initial crack. When a load is applied, the crack in the pure ceramic propagates very quickly, resulting in failure of the material. In the composite, though, the fibers bridge any cracks that form in the matrix, which prevents them from growing, increasing the overall toughness of the material. Unlike polymer matrix composites, where the aim is to have a strong bond between the matrix and fibers, so that loads can be transferred between the two. In ceramic matrix composites, the fibers turbine protect from the extremely high temperatures during atmospheric re-entry. They're also used in the braking systems of stiffness. One example of this is the use of magnesium in biomedical engineering because it's lightweight and has excellent biocompatibility. Another advantage it has over commonly used metals like titanium is that it biodegrades in the body, so a second surgery isn't needed to remove the implant once the injury has healed. But it has quite low strength and biodegrades too quickly to be all that useful. Researchers have found that by replacing pure magnesium with a composite that has a magnesium matrix and a dispersed phase of ceramic particles, the degradation rate can be controlled and the material strength and other properties are greatly improved. Electronic component that dissipates a lot of power. A heat spreader made from a composite with a copper matrix and diamond particles will have higher thermal conductivity than standard materials, allowing you to dissipate the heat more effectively. The composite also allows the thermal expansion coefficient of the heat spreader to be tailored to match the properties of the chip die, which helps avoid high shear stresses between the two. Concrete is an example of a much more common particle-reinforced material, and crushed added advantage of being less composite made called bendable concrete. A is sandwiched between thin skin layers made of a stronger and stiffer material. The lightweight core is typically a foam or honeycomb structure, and the skin layers are either metals, adhesive, like the flanges of an I-beam, one side section, the use of and constantly evolving field in materials science that opens up new opportunities. Composite types will be really important in the design process. Geoswarm runs in your web browser. Superalloys are a class of high performance 1 degrees Celsius, high temperatures, in some cases approaching 1000 degrees Celsius. These materials really are marvels of metallurgy. Carefully selected alloying elements combine to create materials that can maintain strength and stability in the most extreme conditions, allowing us to push the boundaries of modern technology from highly reliable fasteners to jet engine turbine blades. Superalloys can be split into 3 distinct categories, based on their main alloying element. Nickel-based superalloys are the most widely used, offering excellent mechanical properties and oxidation resistance at high operating temperatures. Cobalt-based superalloys have lower strength, but excel in applications involving rapid thermal cycling because of their excellent thermal fatigue resistance. And iron-based superalloys are a lower-cost alternative company, Inco 718. It contains around 50% nickel, 20% chromium, 18% iron, refractory metals like niobium and molybdenum, and small amounts of titanium, aluminum, and a few other elements. L605 is a well-known cobalt-based superalloy, containing 50% iron, 8 to 55 ounces of other elements. Let's take a look at how the yield strengths of these superalloys and more conventional materials are affected by temperature, starting with Inconel 718. It has very high yield strength at room temperature, at around 1,200 megapascals, and its strength is remarkably stable as temperature increases, all the way up to around 700 degrees, where it begins to drop. This is the typical maximum operating limit for this alloy, although some other nickel-based superalloys retain useful strength at temperatures over 850 degrees. A286, an iron-based superalloy, and L605, a cobalt-based superalloy, have lower yield strengths than Inconel 718, but also do a really good job of preserving their strength at high temperatures. Materials, tight temperatures. Materials unsuited temperature, conventional materials. Titanium alloys, for example, have high strength at room temperature, but it drops gradually as temperature increases, making these materials unsuitable for very high temperature applications. Aluminum alloys have much lower strength, and aren't really suitable for use over 200 degrees. And the yield strength of 304 stainless steel decreases steadily with temperature, dropping to less than 50% of its room temperature value at 500 degrees. Another important factor to consider at elevated temperatures is creep, the along megapascal degree. You would temperature carefully in conditions, and they achieve this exceptional mechanical performance and arranging them to the high structure, combining superalloy strengths, high mechanical appreciation at technique and thermal A2A. These fast conventional alloy. Very difficult. And since they're mainly composed of heavy elements like nickel alloy, superalloys is normally limited to situations where operating conditions exception, and this is just the first in a new series of material dives into the puzzles how it's a memory released a fascinating
that we use in space, in robots, and in your mouth. I'm talking about shape memory alloys. Like the name says, these are metals that remember different shapes. To understand how these metals work, we've got to talk about atoms and organizing. Let's talk about atoms first. Atoms are tiny bits of matter that you cannot see with your eye, yet they make up everything in our world, from the chair that you're sitting on to your cell phone. Atoms have some surprising ways of behaving too. We'll talk about that shortly. Now, how big is an atom? Well, imagine put a bus or an airplane, they're all liquid and gas. Many other materials mentioned before. When we say that the metals remember their different shapes, what we're really saying is they remember different seating arrangements of atoms. When the atoms rearrange, the metal moves from one shape to another. Let's look at a phase change in action. Here I have a metal wire that is made out of nickel and titanium. This metal wire is a shape memory alloy, and I'm going to make it switch between its different shapes using heat from a lighter. Watch this. I'm going to wrap this wire around my finger and then heat it. Amazing! That wire returns to a straight line when I heat it. Let's try that again. I'm going to wrap it around my finger and heat it. Yup, that's still amazing. Not only is it amazing, this is weird, because metals generally don't do that. Here's a paperclip. When I heat it, I get nothing. What we're seeing is the shape memory wire changing phases when it gets hot. When the wire is cold, atoms are in a diagonal arrangement, like the movie theater seating we talked about before. We call this a monoclinic arrangement, and scientists will call this phase martensite. When I heated up the wire, the atoms moved into columns, like airplane seating. This is a cubic arrangement. Scientists will call this phase austenite. So when we added the heat, the atoms shifted positions seamlessly, and they'll do this forever. They have this coordinated motion, just like members of a tireless marching band. Each makes a small shift, but altogether, those small shifts create a totally different pattern. So that's pretty cool, but where do we use these materials? Well, if you look in the sky tonight, shape memory alloys are at work, on Mars. They're used to move panels on the Mars rover so that it can study the environment. Like our metal straightened when it was heated, the metals holding the panels will move when electrically heated. When we stop heating the shape memory metal, the panel will return back due to an opposing spring. Back on Earth, shape memory alloys are used to open up clogged arteries as stents, which are small collapsible springs that force open passages. Shape memory alloys are also used to move robots, toy butterflies, teeth and braces, and for a perfect fit every time, shape memory wires are used as underwires in bras. Now you know Victoria's Secret. By popping a bra into the dryer, it'll be brand new every time. How atoms behave allows us to make materials that make our world a better place.
This for young Al, celebrating the monumental task they had just completed. They had just landed a 900-kilogram rover, the size of a Mini Cooper, on another planet. The Mars rover is bursting at the seams with engineering innovation. I could detail the insane landing process and any of the multitude of engineering marvels on board, but today I want to discuss something you may not have put much thought into, something we use every day on Earth: tires. The wheels of the Mars rover have been one of the biggest technical difficulties encountered on the mission, accruing substantial damage through the rough Martian terrain. Surely the engineers at NASA could have predicted this and designed something better. Well, not everything is as simple as it may seem. Even on flat, hard ground, the rover has a top speed of 0.15 kilometers per hour. Yet this snail's pace still has enough force to tear holes into the aluminium wheels of the rover. The engineers have some strict criteria that made the job more difficult. The wheels need to be stiff enough to support the weight of the rover. At nearly 1 ton, that isn't an easy task. The wheels need to be as light as possible to reduce launch costs, and must be able to maintain traction and navigate the unpredictable Martian terrain. The current record holder for the longest journey on an extraterrestrial body is held by the Opportunity rover at 45 kilometers, with the previous record being held by the Russian Lunokhod 2, a lunar rover. Curiosity has racked up just 20 kilometers to date. All Mars rovers have used solid aluminium wheels. The Sojourner, Opportunity, and Spirit rovers all used the design successfully, but the Curiosity rover is much heavier. Each wheel on the Curiosity rover is about half a meter in diameter and 400 millimeters wide, milled from a solid block of aluminium in a similar fashion to the methods described in my Bloodhound SSC video. But unlike the Bloodhound, the Mars rover wheels are milled to just 0.75 millimeters thick over the majority of its circumference. Damage here isn't all that surprising. 0.75 millimeters thick is the same thickness as a credit card. Running a nearly 1 ton vehicle over a sharp rock would be expected to damage aluminium that thick. NASA simply underestimated the roughness of the terrain. More worryingly though, the load-bearing threads, which are about 6.4 millimeters thick, are also damaged, and if they continue to break, the wheels will become useless. The Mars rover cost $2.5 billion to develop, and it employs a nuclear reactor for power. Extending the life of this project was top priority for its engineers, and so finding a solution to this problem has been fairly high on NASA's list for future projects. So what other designs could we use? To reduce the chances of the wheels experiencing a stress that could damage them, we want them to be able to bend and conform to the terrain. This is what our rubber air-filled tires do on Earth. Land rovers drive over similar rough terrain without any major problem. So why not use tires like this on Mars? Temperatures on Mars can dip as low as minus 130 degrees Celsius. On top of this, weight-saving lunar rover used flexible steel mesh wheels with a stiffer inner frame to prevent over-deflection and thin strips of metal attached to prevent the wheel from sinking into the lunar soil. This option was studied for applications on Mars, but the lunar rover had a mass of just 450 kilograms compared to the 900 kilograms of the Curiosity rover. Combine this with the higher gravity on Mars, and it made the wheel unsuitable for the application. The wheels would simply not be able to hold the weight of the vehicle without deforming permanently. But Goodyear, who developed the original lunar wheel, has been working alongside NASA, and in 2010, they were given the R&D 100 award for this spring tire, which could be the solution to our problems. Being both light, capable of bending and conforming to the terrain without permanently deforming, and capable of holding the weight of the heavier rover. So what's its secret? What makes this spring tire different to the ones on the lunar rover? They use a new age material that has some incredible properties, not just for applications in space, but right here on Earth. This spring tire uses a material called nitinol. Nitinol is a nickel titanium alloy that has been named a shape memory alloy, and for for a good reason. You can bend and deform it and then just apply a little bit of heat and it magically returns to its original shape. It remembers its original shape. That is incredible, but nothing is magic in this world and everything has an explanation. Here is how it works. Typically, when a material is stressed, one of two things can happen. If the stress is below its yield point, the material will deform elastically, like a rubber band, and return to its original shape when the stress is released. Alternatively, if the material is stressed beyond its yield point, the material will deform permanently, and when the stress is released, the material will not return to its original shape. So how does this permanent deformation occur? If the bonds are not broken, the material should return to its original preferred crystal lattice orientation, but when sufficient force is applied, small defects in the crystal lattice are able to move. This is what is happening to the wheels of the Mars rover. When driving over pointed rocks and gravel, the stress exceeds the yield stress, and thus the wheels are gradually picking up permanent deformation due to these arranged in such a way when stress energy needed to revert backwards, but nitinol can get that energy from heat. Upon heating, the nitinol forms austenite, an ordered regular crystal structure. Even more amazing and useful is that this transformation temperature can be tailored for different applications. In general, increasing the titanium content of the metal will increase the transformation temperature. This is an incredibly useful property and it has found many applications across many industries. Let's say we want the metal to remember its shape at 37 degrees Celsius, body temperature. Can you think of any applications where this would be useful? I'll give you one. Traditionally, when stents, which are tiny tubes used to clear blockages in arteries, are being deployed, a small balloon is used to inflate it and plastically deform the stent into shape. However, this often places force on the lining of the blood vessel, which can damage it and cause it to form scar tissue. Many stent designs now employ nitinol, which has been tailored to on the blood vessel. Passes a threshold, it actually causes the crystal lattice to transform to austenite, and when the stress is released,